in close proximity, I suggest. So let's have a look. We have a set of 3 screens here. I am hoping you can all see them because the configuration of the room is kind of slightly unorthodox, wider than long.
This is an important announcement. Would the building manager please go to reception? Would the building manager please go to reception?
Very good. I'm sure we'll have other interruptions like that. So yes, the width of this room reminds me of the nature of modern computers. I like to think they're becoming fatter and wider rather than faster in general, but they do offer opportunities precisely for that reason in uncertainty quantification, as we'll see shortly. Anyway, let me just introduce the day by reminding you of the topic here, which is the lofty and very topical one of reliability and reproducibility in computational science. So we're going to be looking at some areas of this which are quite technically sophisticated and applied to a wide range of domains. We're also interested in the broader questions about how you try to approach reproducibility in a best practice and sensible fashion. So one of the points I want to make clear at the beginning is this is an Alan Turing Institute event, and it's funded by the Alan Turing Institute, but it's also co-funded by a European project that I'm leading, which is called VECMA for short, stands for Verified Exascale Computing, particularly for multiscale computing. And the applications here are meant to be wide-ranging, and the purpose of the project, which lasts 3 years, is to deliver centrally what we call a VVUQ toolkit. If you're not, most people probably in this room are familiar with UQ as uncertainty quantification. The V in V stands for validation and verification. So we're in the business of an open source, open development project there, which is accessible already, and we hope people will take an interest in that during the day and beyond. So the things to point out, if you're not familiar with the Alan Turing Institute, I'm very pleased to say that I was part of a Prime Minister's Committee of Science and Technology back in 2011-12, which came up with the idea for proposing such an institute, and its name at that point wasn't clear. It's a delight to know that Alan Turing's name is associated with it. And to just remind you of what it's concerned with, it says its mission is trying to tackle the biggest challenges in science and society with wide-ranging impact and training next-generation scientists and leaders, both in technical, scientific terms and ethically. Well, I'm a West Ham United supporter, and we talk about the West Ham way, but at the Turing Institute, they talk about the Turing way, and that means quite a lot of different things. Like the West Ham way, it's often debated exactly what it means, but they do have a handbook on this, and central to it is the reproducibility of scientific work and managing data. So we're very well aligned with that. VECMA, as I've just mentioned, is all about promoting trust in high-performance computing simulations in particular, as I'll say in a few minutes, for decision-making and many other things. The applications are deliberately chosen to be wide-ranging because the software that we're interested in developing, we believe, can address generic issues across those domains. We'll talk about those during the meeting, and the themes of the workshop indeed include what we call single-scale modeling and simulation, and perhaps a big focus on an area that's largely wide open in research terms today is the multiscale scenario, where you're trying to bridge length and time scales with simulation methods that only work over limited regions. How do you deal with the fact that there are errors in your computations at different levels when you have to move them up and down those length and time scales? So uncertainty quantification is a central issue. It'll come up repeatedly here. There's the wider issue of VV, verification and validation, and an idea of actionable predictions is really underlying all of this. We want to endow our predictions with credibility so that the people we work with who aren't necessarily computational experts believe what we're saying and make decisions as a result. And the last topic is the limits of computing, because a widespread view today in the light of things like the ubiquity of so-called artificial intelligence and machine learning, that you have only to put data or models onto computers and everything that follows must be correct. There's clearly issues there, and I want to discuss those as well. Then that's the program. So I'm doing the welcome address. We've got it's highly varied. We've got invited talks across a range of domains, and then there's some breaks in the afternoon. There'll be starting off an interactive session, 2 parallel sessions, one on software that's being developed by people in the Turing Institute who work on these topics, such as uncertainty quantification. There's quite a lot of that here, and also from VECMA in terms of the toolkit I mentioned. Another 1 or 2 talks, and finally a panel discussion and closing address. So those are the sponsors. I think I've already mentioned them. There are Twitter accounts, and I know there are people already actively tweeting about these things. Please contribute if you're interested. There's a useful information announcement here about fire warnings. I was told the assembly point, if there were a fire announcement, is outside here and down to the left. Look for gate 10. That the exits are marked for toilets. They're down at the opposite end of this kind of large swathe of the building. Again, look for signs. And it's a no smoking policy here. As you will have noticed, we have to follow rules and come in and leave at public opening and closing time. So we will need to be all out of here by 5:30. Catering is served in the Lovelace room. I think that's where people were having coffee beforehand. The slide that talks about the topics, is that coming up, or was it something I jumped over? I can't see it here. It seems to have been missed from this list. But in any case, what I wanted to quickly talk about is why this issue matters to us. Of course, reproducibility in science is absolutely central to the entirety of the methodology, the way of thinking about the world, because the thing that makes science so powerful is its objectivity. Now, I don't want to discuss every word I use, or we'll be in a philosophical wrangle. But science is meant to be objective. What does that mean? It's not a matter of my opinion holding fort. It's a matter of whether we agree, because we're able to do things and get the same results. We share that area of, as it were, human knowledge and understanding. So the centrality of this to science cannot be gainsaid. You need to understand that to work out what it takes to produce reproducible results. I think probably a lot of people in this room are familiar with the 2017 survey conducted by Nature, which was about people trying to reproduce work. And the findings were quite interesting for those who self-selectedly replied. 70% of those who did reply said they couldn't reproduce some other piece of research that they'd read in the literature. And more troubling still, 50% were unable to reproduce their own work, and that suggests serious problems. So that's what some people refer to as a reproducibility crisis. There's a debate on whether there is one, but that's the issue. So experiment is, of course, the ultimate arbiter in a science. People make experimental measurements, and they have to agree with one another, the same observations, so to speak. But we all know the complexity of the real world defeats the notion that we can exactly replicate a single experiment. There are always going to be some differences there because the world is complicated. Random events, different elements that you need to try and take into control. So there's always the need to deal with errors and error bars there, which is, of course, part of the central aspect of reproducibility. In this workshop, plainly we're concerned with the role of the computer in this, theory, modeling, and simulation. And I think because of this ever-increasing uptake of computational tools and methods, ubiquitously, as it were, everyone's using them, whether they were trained in the area or not, this topic becomes incredibly timely to discuss. Where is it relevant? Do I need to remind the people in this audience? Issues as topical and important as predicting tomorrow's weather, let alone the climate in the next century or epochs, depends on modeling and its credibility. There are many other areas, like design and use of existing nuclear reactors. If we're planning on fusion energy, which we certainly are, We need to be able to build those things in a reliable way. This will depend on our ability to handle the modeling and simulation of those setups. And then there's another very important and growing area, which we would call personalized medicine. The whole idea of personalized medicine is that you take data, let's say from individual patients, you process it in some way using computers, and you make predictions. And we want, in all of these cases, something actionable. For the weather tomorrow, it's, do I take an umbrella, get ready to use it? For climate prediction, there are other things you can imagine you might need to do, which are hotly debated. In the medical case, we aspire to make predictions that are actionable in the sense that at the sharpest end, they might be life or death resolving. Believe the result of this simulation and take an action. So it becomes very clear, and that's an area I've been working on quite heavily over the last, let's say, 10 years, how important it is to have credibility in the predictions. So actually, it's all relevant across the entirety of the scientific domain. I've mentioned things which are kind of classically in science, but the areas of importance know no bounds. Finance, economics are part of this, and so too is social science. And migration, human migration, refugees, and so on. This is all capable of modeling, and the predictions from these models have to be equipped with uncertainty, or they won't be taken seriously. So we will be looking at all of those things here today. Machine learning, in the context of this series of talks, is seen as an important adjunct to what people do, but with a firm caveat that it's not to be used as a black box approach. That means I can just get data from anywhere, scrape it up, put it into an algorithm and make a prediction, because there's so many problems with that approach that have been discussed by myself and others that I don't want to go into it now. Rather, it's about the power and strength of those methods when they're used in conjunction with an understanding of the structural characteristics of the problem you're working with. You can then get the data you need and potentially marshal it in a very effective way. It could lead to things like surrogate models that reduce computational cost but retain the kind of uncertainty quantification we're after. So I think that's just a whirlwind tour of why this area is important to us. At the end of the day, we will come back, having had discussions and seen talks by various people, and discuss what we came out of from this with a panel and other closing details, and we'll see whether there's enough interest in this area to carry forward the agenda as part of our group. So I think with that, I can stop and move to our first invited speaker. Do we need to get his slides set up? This is a great pleasure for me to invite Daan Crommelin to give this talk. Dan is a member of the Centre for Mathematics and Computer Studies at the University of Amsterdam. You have a chair in the Department of Mathematics at University of Amsterdam as well. So you're going to talk about uncertainty and unresolved processes. I think your main interest is here in climate prediction.
That's right. That's right.
Right. You've got 15 minutes. I'll tell you after 10 when you have 5 left, and then 5 minutes for discussion.
All right. Thank you, Peter, and thanks more in general to the organizers for putting together this what looks to be to become a very, very nice meeting. So indeed, I will talk about the uncertainty surrogates, and in particular, with a particular interest in applications in atmosphere-ocean modeling, so in climate modeling. Let me mention the sponsors that made some of the work possible that I am going to present. So there's the VECMA projects, where I'm also involved, and there is funding from the Dutch Science Foundation, NWO, that has supported me on a number of projects. Okay, I'll be talking about uncertainties and unresolved processes in a context of multi-scale dynamical systems. And by that I mean, so dynamical systems, time-evolving systems, multi-scale in the sense that there are a lot of processes that are important, that we shouldn't miss out on, over a wide range of spatial skills or time skills, and in many cases both. And so there are all kinds of examples. I've listed a couple of them here. And as I mentioned, for me, climate science is the main application that I focus on in the work that I do. And what these systems have in common is that quite often resolving all the skills that are relevant in simulations, resolving them explicitly, is expensive, and quite often it's too expensive. It's computationally not feasible to resolve everything. And that is an important limitation, and of course people have come up in I guess in all these fields, for sure in atmosphere ocean modeling, dealing with this issue, somehow limiting the range of what's being resolved and somehow compensating for what's missing. But of course the way you do that typically induces uncertainties, and those are the uncertainties that I want to talk about here. Okay, in a very sort of sketchy way, the kind of models that are used for these kinds of problems, you can think of as being a collection of models, right? Modules that cover different skills or processes. So I've focused here on a macro and a micro skill model, right? Interacting with each other. Often the micro skills, at least when it comes to say atmosphere modeling, is actually not one single model, but it consists of a lot of modules, so you can think of it in this way. So there's a lot of little micro skill models that sort of either or not talk to each other, but for sure they talk to the macro skill model all at the same time. And there's interaction back and forth that goes on during simulation, right? So the interaction here is dynamic, so it changes over time. And that makes it a very sort of complicated business to think of replacing these micro-skill models, which are typically very expensive, by something that is sort of cheaper and faster. Okay, and a concrete example. As I said, atmosphere ocean modeling is an important application for me. So here you see a nice figure, satellite image from the MODIS satellite, or the MODIS instrument anyway, of the Earth. So there's a lot of structure. You see a lot of these cloud patterns. These cloud patterns are very important for simulating climate system, and it's difficult to get all the details right of those, and that is because the processes that are involved take place on a small scale. Right? So you can resolve them to a large extent, but with models that are that need to have extremely high resolution, you should think in the order of 100 meters horizontally to cover the entire Earth with a model like that is just computationally not feasible. And as a sort of go-between, here you see this is work from a project that I've run over the last couple of years, embedding, nesting high-resolution models in so micro-scale models in a macro-scale sort of global atmosphere model. What you see here, I'm not sure if it's very recognizable. You see the coastline here of the Netherlands, both here on satellite image and here in this model image. I'm not sure what that red thing there does. And we have nested these high-resolution models. You see sort of 3D renditions of what's happening there. So these are fully 3D large enemy simulation models that resolve all these convection processes, and we sort of nest them in the global model, and they interact right as time progresses. So this can be done, but it's just very, very expensive, right? So here you see, I don't know, I think it's on the order of 70 LES models, right? Just covering the Netherlands. This is sort of a stretch of 100 kilometers. So to do that globally is just way too expensive. Okay, so what can be done? Let me go to a more idealized picture of the kind of models that we're dealing with. So this is a coupled system of differential equations. I've written it here as a system of ordinary differential equations in all kinds of applications. These are effectively discretized partial differential equations, like fluid flow examples, right? And so what's happening, there are two sets of degrees of freedom. There's the X ones for the macro skills. There's the Y ones for the micro skills. And And there's a coupling. There's a coupling which is this R quantity. And it's going to come back in a couple more slides. So keep that in mind. So the coupling, the feedback from the micro scales to the macro scales takes place through this R quantity, which depends on Y and thus implicitly also depends on X. Right? So there's all this interaction there. Okay, now, as I said, resolving all those micro scales, so in this case resolving all these Y degrees of freedom is often way too expensive. So if you use some sort of simplified representation of this feedback, this R, we're going to get uncertainties, right? If we do not resolve all the micro scales in full, we're going to get uncertainties in the feedback. And the main point I want to make in this talk is that if you ignore those uncertainties, I mean, it sounds bad, there's uncertainties, but if you ignore them, it can lead to structural error in the way the macro scales, the X degrees of freedom, are behaving. I have an example model that for some of you may be very familiar. It's sort of an often used sort of test bed, not very high dimensional, but it has a lot of complexities that you'll find in more realistic models as well. So this is called the Lorentz 96 model. It was cooked up by Ed Lorentz, the same one as who came up with the butterfly model that many of you will be familiar with. And it has is maybe not so easy to catch very quickly that this is in fact of the type that I sketched before. So I've highlighted all these interaction terms, right? There's this R coupling, which is here just the sum of the micro scales, and the way the micro scales are behaving is not just completely autonomous, right? It's not independent from what the macro scales, the X degrees of freedom, are doing. Right? There's this coupling, sort of driving force, if you will, for the macro scales involved here as well. Right. So and it's this kind of schematic structure. So there's all these X degrees of freedom that are interacting with each other, nonlinear interactions, and they all talk to these R degrees of freedom. Okay, and if we simulate this, just numerical simulation with, I think this is these numbers here. Right? So there are 18 large scale degrees of freedom, and then 18 times 20 of these micro scale degrees of freedom. This is what you see. Right, so the main point here, so on the x is a scatter plot, on the horizontal is just at one particular value of k, so at one particular grid node, a scatter plot of the value of the macro scale degree of freedom there versus this feedback, this coupling term R. And what you see here is that if you are at any particular value of x, there's not just one value for the feedback, right? There's a whole range of values. There's uncertainty there. And that uncertainty is very important to capture, as I will demonstrate. Okay, now, the thing that we're interested in here is to replace, right, these expensive microscale models by something that is faster and cheaper, right? So by a surrogate. And in view of what I just showed, I mean, the uncertainty in the way this feedback behaves, these surrogates should be stochastic. Because there's uncertainty there. Moreover, it's typically very difficult to see on beforehand what sort of class of models, what maybe family of stochastic models is appropriate to use here. So rather than trying to sort of come up with something heuristic or make a guess at it, we can just try and infer them from data. That the data, right? So we can do limited simulation with the microscale model where the microscales are fully resolved. Take that data and just sort of extract the model from the data. Right? So it's a data-driven approach there. So how can we do that? What's a stochastic model? Well, the aim here is to say, okay, we have these observations of both this feedback, this coupling term, and the associated, right? So at the same time moment, macroscales. And the idea is to sample from the conditional probability distribution, right? So to update, to run, right, our stochastic data-driven model for R, to sample from this conditional probability distribution. Right? So given the past, right, the history of both R and X, right, that specifies, in principle, a probability distribution for R at the next time step. And all, right, again in quotes, all we need to do is sample from it. And of course, right, this history can be very long. So right, we have to resort to approximations, right, truncate it at some point. All right, and again, to stress this point, of course, it's important to keep in mind there's a distinction between random sampling from this distribution and using its average, right? So its expectation, right? Of the entire distribution for R given all these conditions. Of course, you can also just go for the average. That's going to make a difference, as I'll show. All right, with that sort of setup, I mean, this is the kind of construction that we get. We have a full model on the left, right? Everything resolved. On the right is sort of reduced, cheaper model where we have the same differential equation for x here, but it's sort of augmented with a stochastic model for R. Right? So I've put it here as sort of an additive term, this R. So a little more specific than what I showed before, but it doesn't really make a difference here. Right, so what we get is a kind of a hybrid construct. There's an ordinary differential equation, right? It can be physics-based if it's a physical system, or knowledge-based. Sometimes people refer to this as a knowledge model, right? And then augmented with a data-driven model for these feedback quantities that come from the microscales.
Yeah, 5 minutes.
5 more minutes, all right. So what kind of stochastic models can you use for this? So we tried out over time several different ways of doing this. I'm going to show you two things. I mean, this is under development because it's right, challenges, of course, come in when these R and X quantities sort of are high dimensional and might have correlations that you want to take into account. So let me just focus on two sort of more basic ways of doing this that I've worked on with several other people. Developing this. So one is to use finite state Markov chains. There we say all these R quantities, right, these feedback values can only take on a finite number of states, right? And we create a Markov chain, a discrete time Markov chain, to switch between them. The other is effectively bootstrapping, right? So we just resample from the empirical, so the observed distribution that we have. Okay, so sort of the Markov chain, finite state Markov chain way of doing this is something I did a long time ago. Again, this is the Lorentz 96 model. It's the same scatter plots, but now put on top of this are these sort of black boxes. And what this reduced Markov chain model does is effectively jump between these boxes. Right? So there are only, so for every sort of interval of x, there are only 4 possible values, and you can sort of increase that. It makes it a little better, but not too much. So that's the main idea. Jump between these discrete states. And if you do that, here you see results is actually from 8 rather than 4 discrete states at every x value. What I've shown here is in red the probability density function, the autocorrelation function of the full model. In green is what you get if you do this random sampling, right? So the Markov chain. And then the blue dashed one is what you do if you go for the average, so this expectation that I showed you before. And what you see here is that it's important to capture the uncertainty because at the level of the PDF, we're still doing an okay job with the blue one. But when it comes to the autocorrelation function, then we're really missing out on the behavior of the true ACF, right? And I hope you see that the green and the blue, the green and the reds are pretty much overlying each other. So it does a very good job there. 2 more minutes. All right. These are some sort of wave properties. And you see the same picture here. Using the average is really deteriorating the results. All right, so I have some results with the resampling. It's a different type of model that we tried this out on. It's called the Kac-Van-Zig heat bath model. It's one particle that interacts with a heat bath of other particles. And then, of course, the trick there is to, the aim there is to replace all these heat bath particles by one single quantity or low-dimensional set of quantities that sort of represents the interaction with it. Let me not try and cover the details of the model. It's a paper by Andrew Stewart. and Warren from 20 years ago. It's a Hamiltonian system. Main thing here is, again, we have a paper a few years ago to use this resampling, this bootstrapping approach, and if you take into account some of the history of the process, and we've detailed a little more there, shown that it makes a difference between including no history at all and a little bit of the history. We do get a very good reproduction if you take some of the history into account of reproducing the probability distributions and autocorrelation functions. Again, so the long-term statistics of both the position and the momentum of this heat path model. All right, I'm almost at the end. An ocean model application, again, we use this resampling idea there, getting a good, so this is now spatially extended, getting essentially good reproduction of the mean flow field and the variance of the flow field. So I understand time is up.
Sorry.
Yeah, no worries, no worries. I'm at my summary slide. Again, this is the point I've been stressing in my talk. The uncertainties from the microscales do not just induce uncertainties in macroscales. They also have a structural impact, and that impact is important to capture. It does make a difference whether you just go for the average or really try to cover and sample from the uncertainty. On our point, I've focused here on long-term statistics, right? So if you run a model for a really long time, do you get the correct, for instance, invariant distribution, temporal correlations, and so on, which is, of course, a bit of a different focus from looking at sort of short-term prediction, right? That's something I haven't covered here. All right, and as a last remark, these stochastic surrogates approaches, some of these we're working on implementing in the toolkits that we're developing as part of the VECMA project. So that's the VECMA TK toolkit. Okay, let me leave it at that. Thanks.
All right, thanks very much, Dan. There's time for a question or two. Alphonse. Oh, yeah.
Okay, Dan, thanks a lot for your lecture. I keep wondering each time when I hear you speaking, so how much or how can you assess upfront what kind of circuit you would need, or what kind of quality of the circuit you would need given the macro scale model? Is there anything known, or is there any recipe so that we could, or is this still, intuition and gut feeling?
I'm afraid so far it's not completely obvious. I mean, I think in particular when it comes to getting temporal correlations right. So I mean, my intuition, but it's mainly intuition so far, is to include enough of the history of the process, of this R quantity. And if you make that too limited, you're going to miss out on the temporal correlations of the process. But it's something that I'd like to explore a little bit on much simpler, more idealized models to see how that plays out. Right? So there's still a lot of open questions there.
Over there, Hugh.
Test.
Maybe you can introduce yourself briefly when you speak first, so we begin to know who each other are.
Louis Lemieux, I'm a neuroscientist at UCL. Can you put dynamics into this? Could you sort of your summary, your reduction, your surrogate? Can you make it dynamic easily, or is that the same problem?
It is dynamic, yeah, because the
so this cloud, you summarize it in a dynamic way. You could.
Okay, let me just go back a couple of slides then. Right, the idea is to sample from. This is effectively a stochastic process. If you would leave out all these, I hope you can see all that. So if you say, okay, I'm going to sample from the distribution of R at time step I plus 1, conditional only on R at time step I. That would be a Markov process, right? So it's dynamic.
But a property of this can change. That's all I'm getting.
I mean the statistical properties of this.
Yes.
That's right. I mean, if this coupled model will be non-stationary, right?
Okay.
Then,
Okay.
of course, it becomes a different game. So I'm focusing here on the stationary case.
Okay, thanks very much, Dan, for that. We should move on. We've now got a second microphone, and Hugh's moving around with that. That's good. The next speaker is Anna Nikishova, and she's going to talk about, I need to have the title of it. What are you going to talk about? You need to
It's the
get the deck. Anna is a PhD. Anna's a PhD student at the University of Amsterdam, and she's defending her PhD thesis on the 4th of March. She's under the direction of Alfons Hoekstra there. I'm pleased to be her second promoter for that. And there we have the title, Semi-intrusive Uncertainty Quantification for Reliable Simulations. So Anna's main area of research in Amsterdam has been on uncertainty quantification, looking particularly at multiscale models and how you propagate uncertainty between levels. And there's this concept of intrusive or non-intrusive UQ, meaning you can just put sort of wraparounds existing codes. But when we start talking about intrusive or semi-intrusive, it means you have to make certain modifications to the codes you're working on in order to ensure that they adhere to the UQ you're after. So that's what she's about to present, and I'll let you know when you've got 5 minutes left, Anna, okay?
Thank you very much, Peter, for the introduction. So similar as done, today I'm going to speak about uncertainty quantification. And first, I will speak about credibility of computational models, and I will try to define uncertainty quantification within this field. And then I will also introduce you multiscale models. It is a type of the applications I'm working with. Then I will move to method part, and I will introduce you uncertainty quantification. Uncertainty quantification methods we are working with. I will introduce you our multiscale biomedical application. In the results section, I will show you a comparison of the quality of the results obtained with different multiscale models for our applications, and I will finish with some conclusions. So, credibility of computational models is defined by willingness of people to base their decisions on the information which was obtained from these computational models. And in order to build credibility, we need two components. First, reproducibility of our simulation, meaning that other people will be able to copy our simulation and receive the same results, as well as reliability of the computational simulation, meaning that these results will be accurate and precise. And I'm going to focus on reliability part today. So in order to estimate accuracy and precision of our simulation, usually validation and verification, as well as uncertainty quantification are applied. In order to define these terms, let us consider the standard procedure to build computational models when first some measurements of real world are obtained, from which some mathematical models are drawn, and these mathematical models then can be translated to software, which will be result in our computational model. So in this within this step, validation can be defined as a process to measure how accurate is the model, the mathematical model we built. Verification is how accurate is the implementation of this mathematical model. And uncertainty quantification is how precise is the result of our computational model, meaning that both validation and verifications speak about accuracy of our result, and uncertainty quantification is about precision of the result. And today I will focus on uncertainty quantification. So uncertainty quantification is a scientific field which supports decision making using computational models that involve uncertainty. So with this plot, I would like to introduce you a very important problem in uncertainty quantification, uncertainty propagation. So assume that we have inputs to our model, Xi. The model is defined by some abstract function f that depend on these inputs, and then produce output u. And then since usually in real world, measurements of our inputs cannot be done precisely. These inputs contain some uncertainty, and then this uncertainty is propagated through the model, meaning that our output is also uncertain. So in uncertainty propagation, our goal is to estimate, analyze, and if possible, to reduce uncertainty in our prediction. In particular, a very important tool in uncertainty quantification is sensitivity analysis, which tells us the proportion of final uncertainty which comes from each particular sources of uncertainty. This in particular can tell us which parameters contribute greatly to our output. Uncertainty meaning that if we will able to reduce uncertainty in this input, uncertainty in our output will reduce as well. So I am working on multiscale applications, and just briefly introduce you what do we mean with this. So multiscale models simulate processes on different temporal or spatial scales. This scale separation map illustrates an example with two single-scale models, and two important assumptions which we are using are that first, the single-scale model can be considered separately, and second is that usually one of the single-scale component is much more expensive, computationally expensive than other. So, for instance, in our biomedical application, micromodel usually takes much more computational time since we need to run the simulation with a finer time scale or on a finer computational grid. So now I would like to speak with you about our uncertainty quantification method for multiscale applications. So on the slide there are two algorithms which we are using. So on the left is a standard Monte Carlo procedure, which use our model as a black box. And we start by drawing some random numbers from probability density function of our uncertain input psi. We run our model with these values of uncertain output and collect the output. We repeat the procedure n times, and using these collections of n samples of output, we are able to estimate the uncertainty in the output. On the left side, there is illustration of the semi-intrusive algorithm, which where semi-intrusiveness has come from the fact that we are kind of open up this black box, and we are now able to analyze the structure of the multiscale simulation. In this particular method, we are substituting the most expensive simulation or by a surrogate, meaning that first of all, we will be able to reduce the computational cost of our simulation, and the second, since the rest of the components of our multiscale model stays the same, we preserve part of the physics of our simulation, and this will keep accuracy of our uncertainty estimation high. Today we will use Monte Carlo simulation as our reference solution, and we will compare the efficiency gained by the semi-intrusive method with another method to improve uncertainty quantification efficiency, meaning that non-intrusive meta-modeling. The idea is that just with the whole multiscale model is substituted by some surrogate. So today we want to compare these two methods, and with which will be able to produce for us the more accurate and explainable result for uncertainty quantification. I would like now briefly introduce you our biomedical multiscale application. It is a model of instant restenosis. The model simulates the process of narrowing in the coronary artery. So this model contains two single-scale models. One is smooth muscle cells, which simulates the growth of smooth muscle cells in the tissue of the artery. The second model is blood flow model. It is a micro model that simulates the blood inside the artery. We have three uncertain parameters. Our initial condition are uncertain. We have uncertain parameter in macro model, and blood flow velocity in the micro model is also uncertain. Additionally, our macro model is stochastic. And this model simulates the cross-sectional area, which is the free area inside the artery, and we simulate it in time, meaning that we start our simulation by running smooth muscle cell models, which then send geometry to blood flow model, which then updates the shear stress inside the vessel. So each macro time step, which is 1 hour, we receive the result of cross-sectional area, and we run the simulation for 60 days. So as I said before, we will apply three methods for uncertainty quantification, and we will compare the accuracy of our results. So the quasi-Monte Carlo is our reference solution, and the two meta-modeling, we will compare the accuracy. Both of the methods, both of the methods brings us a speed up around 7 times. They are 7 times faster than the quasi-Monte Carlo method. First, I will show you the result of uncertainty quantification. So the right graph showing the mean value and 95% confidence interval in time of the cross-sectional area. The left graph shows the probability density function of the cross-sectional area. Each row is a particular simulation time. So these graphs are quite similar in terms of information they bring. What is important is the black line is our reference solution from quasi-Monte Carlo. Red line is our semi-intrusive meta-modeling, and the blue line is non-intrusive meta-modeling. We can conclude that the both meta-modeling methods produce quite similar to reference solution results, and we see that maybe non-intrusive meta-modeling slightly better. However, we also estimate sensitivity of our output, and now the top graph is semi-intrusive result, and bottom graphs are non-intrusive meta-modeling. So the solid lines are our reference solution, the quasi-Monte Carlo results, and the dashed lines are the meta-modeling estimations. So the top graph, we found that it's quite good approximation. The shadow areas are the 95% confidence interval. So meaning that we can conclude that, importantly, the order of sensitivity measures is preserved. However, when we move to non-intrusive results, we receive this scattered jumping prediction for each time steps, because each prediction doesn't depend on the previous time step prediction. And therefore, we will need to apply the moving average. And we received, thank you. We received quite smooth result. However, it's very important for explainability of our results that if we would receive these scattered results without having this quasi-Monte Carlo reference solution, it would be very difficult to base our decisions on these results. Therefore, our main conclusion is that semi-intrusive methods is more reliable. So, our main conclusions are that multiscale structure of models brings us some advantage in uncertainty quantification. In particular, we can leave some physics inside of the model and only bring the surrogates for the most expensive part of the simulations. In this way, we are able to build more accurate and more explainable meta models. And I didn't speak at all about this research today, but also we able to analyze the only chip components of the single scale model, which then can bring us very important conclusions to again to improve efficiency of uncertainty quantification. I also have some questions. So can we use this multi-component couplet structure of multi-scale models in validation and verification process? And I believe that yes, and I know that already some talks in verification or in VECMA project are made in these directions, as well as I think it's very important to speak about validation of meta models, because uncertainty quantification is a very important topic now in order to build credible and reliable computational models. And it's meta modeling is also a very important part of uncertainty quantification now. So, and we need to answer how to build validation of these meta models. Thank you very much for your attention.
Thank you very much, Anna. Again, chance for questions. Yes. There's a microphone here. Remember, just let us know who you are when you introduce yourself. What you work on is interesting to us as well.
Yeah, hello, I'm Jori. I'm from the University of Amsterdam, and I'm a PhD candidate in the computational science lab, same as where Anna is working. And I work on computational finance. So I understand that in your application you replace a expensive component of the model with a meta model.
Yes.
Of which I would expect that that also introduces some uncertainty. And I was wondering, are you able to quantify the uncertainty that is induced by replacing this component without comparison to the full-scale model?
Mm-hmm. Yeah, I mean, I like to make a distinguish between error and uncertainty. So I would say that we brought some error when we substitute the most expensive component of our model. And I believe that this is a very crucial question. And we really, up to now, it's very difficult to answer how, if we don't have a reference solution, like how much error we brought by introducing this meta model. So I think that your question is very valid. Right now we say no, we don't know, but it's definitely research that should be done.
Okay, thank you.
Anyone else? Yes.
Hi, Eric Daub. I'm an RSC here at the Turing. I'm curious, one of the things you highlighted was that the small-scale model was the more computationally expensive of the two. But you can also imagine there might be some situations where every scale is an equally complicated and difficult simulation. Do you think that there's ways that some of these methods may still be useful there, even if that higher level requires still a lot of computational effort?
Oh, thank you. It's a very good question. So, for instance, in this situation we had like a limit to efficiency we can bring, which is limit since we still keep the macro models, the cost of the macro model which stays there. So in the example you are giving, so basically we will still remain with the 50% of the computational expense of our model, which in some cases can be enough, sometimes probably no, and then maybe in this case, maybe then it's more efficient to use this full black box meta models. So, but it's definitely interesting to try.
Okay. Oh, there's one over there.
Okay, this may be a bit of a strange one, but
you didn't tell
oh, sorry, I'll introduce myself. Hi, I'm Derek Groen. I'm a lecturer in computer science, Brunel University London. I found it very interesting that you didn't only look at the uncertainty using the different approaches, but also about sensitivity of particular parameters. Now, I guess with the semi-intrusive approach, it seems like the sensitivity of particular parameters is preserved a little bit better than, for example, with the Monte Carlo approach, if I understood it correctly. And I was just wondering, because I know about the Sobel indices, and that sort of gives a numerical indicator about the sensitivity, but of course, the sensitivity might not be a Gaussian process, but it could have a certain shape or something, or a certain bias. Are you aware of how we could characterize that, or whether that's even the case? Like I said, a rather offbeat question.
Yeah. So do you mean that like estimation of this sensitivity will have some distribution?
Yeah. So yeah, because so a parameter can be sensitive, and the sensitivity we usually use a number for it, right?
Yes.
But sensitivity doesn't tend to be like a Gaussian process or something. Sometimes it's like a with threshold situation or some other kind of erratic pattern. So hypothetically, it could be that you have two completely different uncertainty quantification techniques that deliver the same sensitivity index, but that actually the underlying behavior of the sensitivity is very different. So I was wondering if there's any technique that we could use to characterize that.
I mean, honestly, I did not look into it, so maybe we discuss this afterwards.
Yeah, perhaps open question. Yeah. I don't know. Okay, thanks a lot.
Thank you.
Okay, let's just thank Anna one more time there. We should now, thank you, move on. Apostos, I'm sure you'll help set up the next talk. The next speaker is Dr. Onnie Luk, who is at the Institute for Plasma Physics from the Max-Planck Society. She works in a place called Garching, which is close to Munich, and she's currently a postdoctoral researcher there, interested in designing tokamaks, which are these fusion reactors for the future, ITER being the big target, which still doesn't exist, but as many fusion things, it's an aspiration. But in trying to design those tokamaks and control the fusion process, there are many levels of, many scales of complexity involved. Multiscale, are you set up there, Apostos? So multi-scale problems abound, and it's probably one of the most complicated multi-scale problems I've had the pleasure of trying to understand here. So Onnie's going to tell us about that, how you control uncertainties in making predictions in that context. I'll tell you when you've got 5 minutes.
Good morning, everyone. So today I will give a presentation on the work that my colleagues and I have been doing, and the colleagues are listed here, basically about the work we do towards validating multi-scale simulations in fusion. I want to start off with giving a little bit of background and motivation of the work we do. So fusion basically is a process in which lighter, positively charged particles fuse together. And in the end, the process produces heavier particles, and energy is also produced. This energy is quite powerful. In fact, that's how the sun and other stars power themselves. We want to bring this sort of energy to Earth. So you may ask, what are the advantages towards this method? Well, one thing is fuel availability. We can actually take the fuel by extracting from seawater and produce the fuel from the fusion process itself. And the other advantage is that it's a clean source of energy, no greenhouse gas, and no long-lasting radioactive waste like fission power plants. So in order for fusion to happen, we need to heat up these positively charged particles, or we call plasma, to about 100 million degrees. And that's, well, the sun, for example, has mass to its advantage. Because of its mass, it can use it to use gravity to actually confine the plasma, but we don't have that sort of advantage on Earth. So we have to come up with clever ways to confine the hot plasma. Some of the ways that are notable are magnetic confinement, so basically using different magnetic geometry to try to confine the plasma. And another notable confinement is inertial confinement, basically using lasers to heat up a pellet filled with fuel and then basically use it to compress and ignite to create fusion. As Peter just mentioned earlier, so tokamak is actually the best scenario we have towards a fusion reactor. And so there's international collaborations going on called the ITER projects to try to build an experimental fusion reactor to demonstrate feasibility of fusion plasma. And the expectation is that we will produce an output power of 10 times as much as the input heating power. So that's great. However, there's a saying in the fusion community that fusion's always 50 years away. We have been spending decades, so long, working on this problem. Why is it so difficult? Well, we found out that there's micro instabilities that build up inside the fusion plasma that can ultimately destroy confinement. Basically, it alters the overall transport of the plasma and can destroy confinement. So that's bad news. So to give you a little bit details of the scale disparity of the problem, if you look at the turbulence I said that creates the instability, is right here, and versus the transport, it's actually over there. So if you look at the spatial and temporal scale, they're widely disparate. And so what we need to do is create a numerical model that can tackle both, simulate both phenomena. So my colleagues and I have been working on a multiscale fusion workflow. Basically, what we do is take the component-based approach and couple single-scale models together. And this allows information from one single-scale model to pass on to the next. So as I said earlier, there's a turbulence problem, and then there's a transport problem. So it can actually pass, the transport model can pass core profiles that it calculates to equilibrium code, to the turbulence code, and equilibrium code can actually can update the equilibrium geometry based on the core profiles, pass it on to turbulence code as well. And using those information, the turbulence code calculates the fluxes, and ultimately we use the module to convert these fluxes to transport coefficients that are relatable to the transport code, and then we update the core profiles at the transport model, so on and so forth. So we have used this multi-scale simulation workflow and did some simulations basically tackling problems about time scale bridging and also studying the plasma quasi-steady state, in particular the core profiles. So these are some of the plots that we have, including time history of fluxes and temperatures, and we're looking at how the temperature looks like at quasi-steady state. Now, yes, we built this multi-scale fusion workflow and we have simulations, but how does it compare to experiments? Is it good enough? What should we do to give ourselves a good footing or a good place to decide whether we have a good enough model? So there are a few steps that we want to take. Is we want to make sure that we want to verify that the simulation can correctly implement the model, the conceptual model, and we want to validate against the experimental data. And also we want to quantify the uncertainties in inputs and outputs, and the outputs in particular would be the core profiles. In other words, VVUQ, which Peter mentioned also earlier. So let's jump to uncertainty quantification first. Uncertainty quantification is the discipline that seeks to estimate uncertainty in the model input and output parameters, to analyze the sources of these uncertainties and to reduce their quantities. So in our FECMA projects, we come up with several uncertainty quantification patterns for multi-scale models. And right now I'm just going to mention two of them. One of them is non-intrusive UQ pattern. So what we do is treat the entire model, in our case would be the multi-scale fusion model, as a black box. We don't touch it, we don't alter anything. And what we need to do is define the uncertain inputs, feed it into the black box, and then we look at the outputs, which would be the quantity of interest. And then the other method would be semi-intrusive, meaning instead of taking the entire workflow as a black box, we actually look into each one of the single-scale models and treat those as black boxes. And then we study the input and the outputs of each one of these black boxes. So for this presentation, I just focus on the non-intrusive pattern. So in our model, there are two kinds. There are two kinds of uncertain inputs. In our model, the external one is basically the applied heating sources, and boundary conditions. As you can see here, labeled in or colored in gold. And the internal uncertainties would be coming from the turbulence code. Turbulence code, which is where we see the stochastic behavior. And so for the quantity of interest, we are, again, like I said earlier, look at the electron and ion temperatures coming out from the, from the transport code. So because we're looking into the internal, non-intrusive method, so we decided to focus, is it me? I'm sorry, is it me? Okay. So we decided to focus on the external uncertainties only. And what we do is that we take the EasyVVUQ library from the FECMA toolkit to perform the uncertainty quantification. So EasyVVUQ library is a Python-based library, and it basically helps users to facilitates the process of doing uncertainty quantification of models. And so what happened, so as a user, all I need to do is provide the parameter description and define the UQ method that I'm interested in. And then I send it to the EasyVVUQ library, and then EasyVVUQ library would take the parameters and create samples and then run the simulations and gather the statistics and provide me, as the user, statistical moments such as expected values, standard deviation, variance, and sensitivity indices. So the method that we decide to use at this moment is the polynomial chaos expansion. So what it does is that it approximates the quantity of interest as a summation of polynomials orthogonal to the input distributions. And then using these values, we can figure out the statistical moments as well. The advantage is that it uses less samples compared to Monte Carlo method, for example. And then the disadvantage is that there would be truncation error introduced when we do the estimating, when we estimate the uncertainties. Oh, okay. And then for SOBO indices, SOBO sensitivity analysis, it is basically it helps quantify the uncertainty. It calculates the indices that give us the sensitivity of the quantity of interest with respect to the input parameters. So first order would be the ones that quantify the direct effects on the outputs based on the input. And then the higher order would actually look into the interactions between the uncertain parameters and how it affects the output variance. Okay, so to give you an idea of what we do with all of this, so what we now have is that we define the uncertain parameters. We said, okay, we have the applied heating sources, which is a function of a Gaussian. So there's three quantities that characterize the Gaussian: amplitude, position, and width. As for boundary condition, we define the temperature at the edge of the plasma. And so therefore, we have 4 uncertain inputs. And we also give a description of each one of the parameter. They have a normal distribution with plus minus 20% around the original value. And then, so like I said, we use PCE method, and we take 6 sample points from the distribution. So for each uncertainty input, that means 1,296 samples. And we are interested in the temperature profiles from the transport model. So let's apply all of that to the electrons first. This is the result we obtained from our UQ on the workflow. So here you see that the electron distribution, the electron temperature distribution, we have quite a deviation, which is labeled in blue. We have quite a spread at the what we call the core of the plasma, but then it damps out, or it narrows down at the edge of the plasma. what I think is interesting is the first Sobel indices. When we do sensitivity analysis, we look at each one of the input parameters and see how sensitive it is to or how the variance of the output, depends on the input. So you can see that takeaway is that the width of the heating source actually doesn't affect the variance of the output much. So we can take that as, okay, next time if we do UQ, we don't need to take width as an uncertain parameter anymore because it barely affects the electron temperature profile. And of course, we see that the boundary condition, which is the temperature at the edge of the plasma, has a big influence on the variance on the output. And then for position, we see that it mostly affects the the core of the plasma, so on and so forth. Now we do this again, but except now we look at the ion temperature profiles. What we see here is, so this is the temperature distribution, temperature profile with the mean and the deviation. We don't see that spread that we saw in the electrons temperature profile. And then here we can also do the takeaway of the width. Doesn't seem to matter too much when we do uncertainty quantification on, or the variance of the output. So the next thing we did is we take these UQ results that we obtained, and then also we look at the result that I present before any UQs is inserted into our simulation, and compare all of that with simulation results. So what we do is we take some of the data coming out from the ASTEX upgrade token bank located at Max-Planck Institute for Plasma Physics in Garching, and we take 2 of the experimental shots. So the experimental shots are colored in purple and green, and then the UQ results that I mentioned earlier are colored in thin blue line and a red and red. And and then the results that I present earlier before any UQs is added in is in thick blue line. So let's focus on the left panel. So the left panel is the ion temperature profile. We can say that looking at the overall picture, the results seem to agree fairly well. However, if we move on to the right panel, the electron temperature profile, we see that there's a big disagreement from the core of the plasma towards the middle of the plasma profile. So why is that, you may wonder? I did mention earlier that the UQ results that we're using an analog turbulence model, meaning it doesn't have any, it's very simple. It ignores a lot of the stochastic, behavior in a turbulence model. Versus the results that I had before any UQ is introduced, those results is using a stochastic model, a more sophisticated model. So you can see that as the more sophisticated model, which uses gyro fluid theory, it actually gives us a better estimate of what the experiments look like versus the analog model. Okay. Right, so as a summary, so what I want to say is the fusion process is very difficult to understand because there's micro instabilities that affects the confinement of the plasma, and it can ultimately destroy the confinement, and that's what makes it really hard to achieve to showcase the feasibility of fusion plasma. So we introduce a simulation model that takes the microscale model and the macroscale model together and to study this multiscale problem. Non-intrusive UQ and sensitivity analysis are performed, and we also take 2 experimental shots to compare the results that can help us prepare as part of the VV effort. What we see is that while the ion temperature profiles show more agreeable results, the electron temperatures around the core area doesn't. So we want to continue our routes into the VVUQ, and we want to use that to give us a better understanding of the simulation performance compared to the experiments, and then so that we can move closer towards validating in a workflow. And I hope I can convince you today that this work can easily also be extended to other simulation, fusion simulations or any other multi-scale simulations. You can introduce different workflows. You can study it, how stellarator plasma behaves, or how inertial confinement physics look like. As for outlook, as I said a few slides ago, there's a semi-intrusive UQ pattern that we also want to explore. That way we can understand how error from one model propagates to the next. And that way we will include the intrinsic uncertainties coming from the stochastic model as well. So that will give us even a more suitable model to study compared to experimental results. There's also something called a QCG pilot job in the FECMA toolkit that we would like to use to execute many subordinate jobs in a single scheduling system allocation. That will help us a lot when we study the stochastic turbulence model. And of course, we want to expand on our methodology in the validation and verification part of our studies. Thank you very much.
Onnie, I want to apologise a bit. We have those sound problems, and the engineer here advised me that that's caused by someone next door also starting to use a powerful system. We'll try and resolve this by the next session. Okay, running slightly over, so pressing questions. I can see one over there, Hugh.
I don't know, maybe. So you're not trying to save computational time. You're trying to simulate a physical system, correct?
Well, I mean, we also want to save computational time too.
Because why? Why would you?
Well, for example, when I set one of the parameters in the heating source, the width of the Gaussian function, it doesn't seem to affect the variance of the output. Then we said, well, next time when we do sampling, we can reduce that doing dimension reduction, and that will help, for example, save computational time. Also, we also will probably explore surrogate models as well, so that way it's another route we can take to reduce computational time. But that's not exactly our major focus, but that's something we're interested in, just not our major focus.
Okay, I think it's good to stop there. We're going to have a break now. We're just slightly overrunning, so I suggest we'll get back here at 11:40. Where we're going now is the Lovelace room, where we had coffee if you arrived early enough in the morning, back there. And then back here at 11:40, there'll be one more talk, and then there's a discussion period during that, so we can catch up with things in detail. Thanks again, everyone who spoke this morning.
bothers. Anyway, welcome back. My name is Alison Heppenstall. I'm from the University of Leeds. I'm one of the organisers of today. So we're going to have a presentation in a moment, followed by a discussion, which I'm kind of going to make up on the spot, but I'm going to invite contributions from. So it's my pleasure to introduce my colleague, Nick Malleson. We're both in the Urban Analytics programme, so we're coming at this from a different perspective, which I'll pick back up in a moment. And he's going to give you a flavour of the type of work that we're doing up in Leeds.
Thank you, Alison, and thanks, Peter, for organising this. So my name's Nick Malleson. I'm a geographer, actually, so I did my PhD in computer science and then moved into the School of Geography. My undergrad was in computer science, PhD was in geography, so I've kind of got a bit of computer science, but now it's mostly a geography, and you'll see that from the absence of equations on most of these slides. So this talk is going to be a little bit different from the first three. It's kind of looking at less fundamental work, but it's been really interesting to see some of the ways that people are dealing with uncertainty quantification from a very kind of fundamental level, and I think there's a lot of overlap between the kinds of things that I want to do and what we're actually able to do experimentally, and how we might learn from the more fundamental methods, and maybe that's something we might discuss afterwards. So this is work with my colleagues, Alison, John Ward, Robert and Min, who are the kind of the brains behind the work. They can do the hard maths, which I've taken off these slides so I don't have to explain it. And the talk's going to be about how we can try and reduce uncertainty in simulations of social systems through data assimilation methods. If anyone has these slides, there's the abstract and the links to the papers that kind of underpin most of the work. Okay, so in terms of a bit of background, if we take a social system, people moving around a city, for example, we usually have very good data about the people who live in these places. So somewhere like Trafalgar Square, we know who lives there from the census. We know lots of information about the socio-demographics. We can look at hotel records to see who's staying there. What we don't know is about the people who are visiting. So we don't know what these people are doing in Trafalgar Square, how long they might stay there, where they might go next. So if we were able to build a model of these daily movements, these kind of quite fine resolution movements, it could be really useful for things like understanding how cities actually work. So we could manage busy places better if we knew more information about what was happening in them at the current time. We would be better able to manage emergency scenarios, because if we start off with a better model of what places look like now, then our short-term predictions of how emergencies might play out will be better. And yeah, a model that's built on current data is going to be able to make better short-term forecasts. So there's lots of reasons why we would like to be able to build simulations of social systems and then feed data into them, which is something that for agent-based modeling, which is the method that we're working with regularly now, which is something that you can't do yet. So a lot of this work is about looking for those methods. The reason that this is problematic is because even if we have a fantastic model, so I mean we don't have very good models of people. People are really complicated. But birds is maybe a better example. So we might have a really good model of how birds flock and how they interact with other birds. We might have really good initial conditions for our flock. So accurate to the nearest centimetre of where the birds will start. But if we wanted to simulate that flock, within seconds, maybe minutes if we're lucky, our simulation is going to diverge hugely from the real flock. Because of the uncertainties present in the model of the birds, the input conditions, and maybe some parameters that will evolve as the world evolves. So in effect, to be able to model these kinds of systems, a flock of birds, people moving around cities, we need to be able to incorporate real-time data to update our model in runtime. And this isn't new. So the idea of data assimilation has been used by meteorologists and others in the physical sciences for decades, and they've developed some really clever methods. And data assimilation is one of the reasons that meteorology weather forecasts have got so much better in recent decades. And what they do is they assume that although we have relatively uncertain data, so our observations are noisy but they're pretty good, the observations are very sparse because we only have limited sensors in the world to detect things. We also have models which are much more detailed, so our models can sort of fill in the gaps in between the data, but the models have much greater uncertainty associated with them. So the idea behind data assimilation is to be able to take the uncertain or the less uncertain observations, the uncertain models, and bring them together, and then you should get something better than either the data on their own or the models on their own. And as I said, there are some really good methods to do this, but it's not clear how well they will apply to agent-based models, which are fundamentally very different to the kinds of models that you would get in meteorology or the other sort of hard sciences. So where we want to get to ultimately is to be able to simulate a city. We'd like to be able to build a model that has people in it doing their typical things that people do, commuting, leisure, etc. They could be taking different modes of transport, they could be doing different activities, and what we would like to do is build this model and then start to feed it with data from different sensors. So it could be things like traffic counters, it could be pedestrian footfall counters. You could look at the population density estimates in real time from the volume of calls that are going through mobile telephone masts, etc. So there's a huge, diverse sets of data that we could use to try and feed these models. And that's where we'd like to get to ultimately. But that's way too difficult for now. So we've scaled it back a bit, and we're just looking at trying to simulate relatively small crowds. So if we wanted to simulate a crowd, do we have enough data to sort of look at where people are, maybe track some people, maybe not, and then build a simulation based on those parameters. And so this is what the two examples I'm going to show in this talk are about. What we're interested in finding out longer term is what kinds of data do we need? So as I said, do we have to track everyone in a crowd to simulate them, in which case the model is not quite redundant, but nearly redundant? Or is it okay to just track a few people and try and work out what everyone else is doing from them? Or even better, can we just take aggregate data? So can we count the number of people who enter and exit different parts of the space? Can we measure the population density? Some of these aggregate measures. And these are all the kinds of things that we want to experiment with. And we're doing that for the moment with a very simple hypothetical model. So this is something we've called station sim, and it kind of loosely represents a train station. So you could imagine a train arriving on the left and the people leaving the train carriage, and they're moving across the station and trying to leave from those exits. And the interesting thing about this model is as the agents collide, you start to get crowding. And the crowding depends partly on the behavior of the agents, which we'll come on to, but also the sort of random choices about when they leave and which exit they want to go to. So it's a very simple crowding model. It doesn't try and compete with some of the comprehensive agent-based crowd models. But the nice thing about it is we know exactly where the uncertainty comes from. The uncertainty comes from when the agents collide. So if there's a slow agent holding up a fast agent, the faster agent tries to either go to the left or to the right to try and get around the slower agent. And that's the only randomness in that model. So it's really easy for us to try and do data assimilation on that model because the uncertainties are so easy to understand. Okay, so for the next two examples, I'm going to show you us trying to do some data assimilation on this relatively simple crowding model. The first example is going to be with a particle filter. So most people are probably familiar with these. It's a brute force ensemble method. The nice thing about it is it doesn't require any assumptions about the underlying structure of the model, which is good because agent-based models are not usually Gaussian. What you do is you create a number of realizations of a model. So we might create 1,000 individual agent-based models, and you run them concurrently until you get some new data. And then when you get your new data from the real world, your new observations, you look at each particle, see which of those is doing well, which are doing badly, and then you reweight them according to how likely they are to have produced the observations that you see in the real world. So the idea is each time you do a data assimilation window, you can remove the particles that are doing badly, resample from those that are doing well, and then continue. And so this sort of shows that. As I said, we're not applying this to real crowds yet, so our real-world data come from one run of our agent-based model. So we run that in isolation, generate a load of data from that, and then we then feed observations from that pretend reality into the data assimilation algorithm. Okay, so that's how the particle filter works. Just to give you an example of what it's actually doing, this is a plot that shows where some of the agents in one of these runs are. So those two black squares are two example agents from a run with, I think it had 50 agents in it, this one. I'm only showing 2 of them. Normally we wouldn't know where those agents actually were because you wouldn't get that in the real world, but because we've generated all of this data from our model anyway, we know where the kind of pseudo-real agents are. So those 2 black squares are 2 example agents. There are others in there that you can't see. And each of those little red dots is a particle estimate of where that associated agent is. So it's at the start of the simulation, most of the particles are doing pretty well. The red dots are sort of centered around the black squares, so the particles are estimating the locations of those agents quite well. When I go on to the next slide, you'll start to see the agents move across the screen, and as the model evolves, the particles, some of them start to do worse and worse. So some red dots will still be clustered around the black squares. They're particles that are simulating those positions well. Others will start to diverge. And then when you start your data assimilation window, you'll see lots of those bad particles are sampled out, and the estimates of those locations get a lot better. So in this way, you're able to remove the poorly performing particles, and the population as a whole improves. And in simple situations, it works really well. So in a simulation with only 10 agents, this is after 100 iterations, so those 10 agents have moved most of the way across the room. There's very little interaction, so there's very little uncertainty, so most particles are easily able to guess where those 10 agents are, because it's basically a linear model. It's not quite. I mean, some of them are slightly confused, but mostly it's fine. If we increase the number of agents, though, we get many more interactions. There are many more possible evolutions of the model, and you can see that the particles start to do much already. Oh, yeah, okay. Much less well. So this agent, for example, in the bottom, it's not a great example. This agent here, the one to the furthest to the left, all of the particles are estimating pretty well where that agent is, and that's probably because it hasn't interacted with anyone. Some of the others, you can see those long back lines are linking the particle estimates to the actual locations. They're totally out. So there are some particles there that have chosen, by chance, totally the wrong evolution of this system. And the problem here is we still only have 10 particles, 40 agents. There are many thousands of different ways this model could have evolved, so the population size is way too small. And then this graph sort of shows that that can be mitigated by increasing the number of particles. So in this bottom right-hand corner, we have large numbers of agents and very few particles, and you have high error. As you move to the top left of that graph, you have fewer agents, more particles, you get lower error. The point is that if you have enough particles, this method will probably work in this sort of situation. The second example I want to show you is an uncentered Kalman filter applied to the same problem. Kalman filters are pretty popular in meteorology and some of these other fields. They should be more efficient, but it does rely on some Gaussian assumptions. So one of the things we're really interested in is how well this is going to apply to agent-based models. In an uncentered Kalman filter, a few sigma points are chosen to represent the model state. So instead of having a very large ensemble of particles, you can reduce it to a few sigma points. And if they're chosen well, it can be really efficient. A load of complicated maths happens, which I've skipped over because John and Rob understand that and I don't. Ultimately, the really interesting thing about the uncentered Kalman filter is it's very good at inferring the positions of unobserved agents from those of observed agents. So what this graph shows is that when we observe the agent, the Kalman filter does pretty well. All of the red squares are kind of overlapping with, so the real locations are overlapping with the estimates, which you'd expect because we're telling it where the agent is with a bit of noise. But the really interesting thing is some of those observed agents are also doing very well. So if you have a group of agents all moving together and you only observe one of them, the Kalman filter is able to estimate the locations of the other agents that are near the observed one by some clever covariance, which you will have to ask Rob about if you want to know how that works. And this just gives some more evidence for that. In the very last example, I want to switch to a different situation. This is bus simulation using a particle filter again. The idea here is that if we know where buses are, which we often do, they all have GPS locators in there now, we have quite good observational data, but we don't know other things about the bus system. So we don't know where people are waiting, we don't know how many people are on buses usually, because we don't tag them as they get off. We don't know what the surrounding traffic levels are. So actually building a model that predicts short-term bus behavior into the future can be quite hard. So my colleague Min has built this bus simulation, which is quite nice. It's, it's a simple one. This is based on a bus that has its own track, so it doesn't rely on surrounding traffic levels, but this would work with surrounding traffic levels as well. And he applied a particle filter to it. And this video shows that. So on each of those diagonal lines is a bus that leaves the depot on the bottom of the horizontal axis, and then it travels away from the depot over time, which is that movement up to the top right-hand corner. And basically what you can see is the particle filter estimates the location of the bus pretty well. I mean, you'd expect that because we're telling it where the bus is. But the important thing is the future predictions are also pretty good, and they're much better than you would get if you were just using a model without any data assimilation. So the implications there are that we could estimate how long it's going to take buses to get to bus stops much better. They do that really well in London, but outside of London it's pretty rubbish. So that could be a really useful method for improving the transport system for users. Okay, last two slides. I just wanted to mention some of the ethical implications, particularly with modeling urban systems. If we're going to be using more sort of novel crowdsourced data, things like Twitter or social media contributions, we need to be very careful about data biases. So the digital divide will be a real issue if we're using these kinds of data sets. We don't want to build a model that represents people who are online very well, but forgets about everyone else. And one of the advantages with these kinds of models is I think we'll be able to do them quite well just using aggregate data. So in these examples, we have looked at tracking people, but ultimately I think we won't need to. If we have good aggregate counts of people, then we won't need to worry about actual tracing of individuals, which is much better, I think, than trying to track people as they move through spaces. Okay, so to conclude, we are building agent-based simulations and trying to feed them with real-time data to keep them up to date with the real world. Surprisingly, this is really hard to do and hasn't really been done particularly well. Or efforts are ongoing, but it's very early days. So we started to experiment with some well-used mathematical models from fields like meteorology to try and do data assimilation, and we're starting to learn about how well they apply to agent-based models. And ultimately, we'd like to work towards a larger urban model of urban flows. Okay, thank you. Oh, sorry, no, one more slide. This is how you can have more information about what we're doing. Most of the work is funded by the ERC DUST project. It aligns closely with a Turing project called Uncertainty and Agent-Based Models for Smart City Forecasts, which is starting next month, and also aligns closely to Alison's Turing Fellowship, which is looking at using AI methods to uncover patterns in cities. Okay, that was it.
Any questions?
Just a quick one. To me, the obvious data set to work on is the London Underground tube system, where our MAC address is. So they're getting several million data points a day. Have you had a chance to look at that or work on that sort of thing?
We have some colleagues who have done a lot of work with TfL. I haven't been able to access that data. I don't think it's publicly available.
No.
No. So they would be, yeah, you're right, they'd be a really good organisation to work with. I would like to.
Okay.
Thanks.
Thank you.
There's the Oyster card data as well.
No, that's quite trivial compared to the Mac stuff. It tracks your phone.
Yes, yeah, okay. Yeah.
Oh, hang on. It's Ellen there.
Thank you for your lecture. So indeed, when are you going to apply this to real data? But coming back to the rail station example, I'm aware of some work done by Professor Verdicchio in the Netherlands, who has been actually measuring movement of people in the train station in Eindhoven. And two things. One, he was able to, in a statistical sense, to use Fokker-Planck equations to describe the density of this crowd. So are you really in need for the kind of questions you want to ask to your model? Do you really need to follow the individual agents, or could you use this data to parameterize, say, a Fokker-Planck model? And then what would that mean for your uncertainties? So lots of questions. But
yeah. The second question, no, I would like to, afterwards, I'd like to write down the name of your colleague. So the advantage of agent-based models is you can, so I mean, I haven't read your colleague's work, so I don't want to presuppose some weaknesses, but typically the reason you'd use agent-based models is you can better include heterogeneous behavior, so different behaviors of people in the crowd. So that would be the reason that you might want to use an agent-based model over that. But I'm sure actually for an empirical study, that work is probably further along. So if you...
But aren't humans extremely boring in big crowds? I mean,
not necessarily, no. I mean, so the way that people react to emergencies, or the way that kind of, I mean, if you look at the difference between a protest and a riot, those kinds of things emerge quite interestingly. So, but I do take your point that if we wanted tomorrow to have an empirical application that someone could use, we probably wouldn't use an agent-based model right now. We'd probably go with your colleague's work.
When asking questions using this little thing, can you hold it up to your mouth?
And can I just answer, you said when as well? So in terms of bus simulation, that model is ready, it's been published. We're really keen to work with someone on any real data, and I'm kind of trying to find bus companies who will work with us on that. In terms of the crowding, I think we still need to answer some more fundamental questions about how well the models will work when we start to scale up, so when we move from 400 agents to a few thousand. So in terms of crowding, when is a little way off yet.
we have lots of data on people moving around in the Amsterdam arena, so the football stadium. So
okay.
you may want to talk to these people.
Yeah, do. I'll come and write down some names. Thank you.
Okay, so how close do I have to get? It's a great fun thing, but so assimilation works in meteorology because you're in a continuum, and there's a decorrelation length scale. So you know that what happens over here is telling you about what happens over here, and I can see that buses are probably in a continuum. But when I came through St Pancras this morning, I'm not sure the crowd was in a continuum at all. It was a very random people moving around. So I can see how agent-based modeling works, but assimilation, is it relying on some sort of continuum property that you don't really have?
Some of them are, yeah. So this is one of the things that we need to. The Kalman filters do rely on this kind of continuous, and I'm really pushing the limits of how much I know about these methods now. So bear with me. But yes, the Kalman filters do have some assumptions based on things like being able to differentiate the surface, which probably don't work for some agent-based models. We need to experiment though to find out, I think, what the implications of those assumptions are going to be. Particle filters, probably not so much of a problem, but they are a much more computationally expensive way of solving this.
Another one final question? Someone right over there? No? In that case. One more.
Just following up on what you just last mentioned. So the particle filters tend to be very expensive for systems with many degrees of freedom, right? So this is also a limitation, I think, in meteorology to apply real particle filters and say at an operational level. So how do you see that in your application? If you go indeed, as you mentioned, from a couple dozen to a couple thousand, or maybe hundreds of thousands of agents, but what are the prospects there, do you think?
One of the interesting you should ask that. We are having there's another Turing-funded project has started in January, where we're trying to port the model to GPUs so we can leverage some of the massive GPU clusters that places like Cambridge University have. So that, because the model is still relatively simple, it's not that complicated, that it would run quite nicely in parallel on a GPU. I think we would like to explore running particle filters with millions of cores. That would be the first place to look at that. I mean, we may hit a point where we can say categorically that with current computing power applied to something that isn't, frankly, as important as simulating global weather patterns. I mean, people walking around King's Cross is important, but within reason, we don't want to take a whole HPC just to do that. We might be able to say that particle filters aren't ever going to work for now anyway, but we're not there yet. I think I would really like to explore some of these highly parallel methods and infrastructure before we say that.
Do you think it would be, if you go to say continuum description, that this would, right, which would maybe even be the more appropriate, the more particles the more agents you have in your model. So you go to a sort of a continuum limit almost. That it would work better there.
Sorry, I'm not sure.
Well, say a fluid description of all the agents would lend itself better to particle filtering.
Yes, I mean, I guess the issue there would be the individual heterogeneous behavior that you couldn't capture in the same
miss
way.
out on.
Yeah,
Okay.
Yeah.
Yeah,
but no, that's a fair point.
Thanks.
Thank you. Is this working? Go back for the blue box. Thank you, Nick. Nick, can you stay up for a moment? Can you just switch back to your Trafalgar Square slide? I'll use you while you're here. And that was a really useful question, because we're now moving into discussion, which we have about 15 minutes to go on time, and we will not be late for lunch because I'm from the north and I'll get hungry. Nick and I are both from the Urban Analytics program, and Nick's talks sort of nicely articulated the approaches we're trying to take to quantify uncertainty, do calibration and validation. Now, we work with a technique, agent-based modelling, and this is quite nice because if we were to use agents, simulate every person here, give them rules, put them in the system, it's nonlinear, there's feedbacks, it's stochastic. We want to know what's happening. We also have scale problems as well. Dan was talking about scales, micro to macro feedback within there. We have all these problems. Now, the one big opportunity I think this forum could have for us is that we do very little about quantifying uncertainty. Our calibration and validation in agent-based models is sort of a black art. It tends to be an SRMSE or an R squared. Maybe some visual validation as well. Because, of course, these systems are spatially and temporally dynamic as well. So how do we recognize what the uncertainty is in our models? How do we handle that over our dynamic simulations? How do we improve these models? Now, we want to do this, and we're really keen to take all your fantastic ideas we've heard this morning, because there's a huge opportunity looking at aging populations, transportation infrastructure, energy, sustainable cities, for policymakers to use our models. But at the moment, we can't say to them, if you make all your transportation free, you'll reduce down impacts in HS through exposure to air pollution, improve your economy, and we're X% certain this will happen. We don't currently have those methods. So the sort of brief discussion I would like to have with you, and I might pick on individual speakers to have their opinions as well, is how can we, with our problems, take your methods and bring them in? How do we make that bridge? How do we join up all this fantastic work to help us deliver our digital twin idea?
Well, I could use this one. Very briefly, because Derek loves talking. Derek is the one member of our... over there, the one member of our team who works on social science applications. It's human migration and refugee modelling using agent-based models. And you must be a good link between us and them, Derek.
All right, well, I guess that's my cue to say something, but I was raising my hand anyway. In my group we model migration, slightly different setting. It's more in African countries, people escaping conflict, trying to find safety. The first thing is to really be very clear about the area of applicability of certain simulations. At least in my case, I found that you can construct an agent-based model to resolve a very specific problem. And then if you do that, you basically, you have data to validate against, and then you develop your model. Now, with letters Boltzmann or N-body or molecular dynamics, you have all these nice physical laws you can count on, right? With agent-based modeling, you don't, because we can't just cut open a brain and get the rules out. So one thing I'm actually really interested about, and which is very much, I think, in relation with uncertainty quantification, is about how the assessment of sensitivity of individual parameters can guide model development. So for example, if I have an agent-based model and I have a rule, and it turns out that that one rule in my 200 rules of my agents, although most models have fewer, but has 90% of the sensitivity, then that would give me an indicator that I should actually perhaps use something a bit more advanced than that one single rule. So I think in the first instance, I think sensitivity analysis and perhaps also uncertainty quantification could guide the model development. Then on putting the error bars on the model so that you can tell a government, so in my situation, in our situation, it would be like, okay, there's a 20% probability we expect this many people to arrive or that many people to arrive. That's quite hard because I guess you need to validate the uncertainty as well, right? So then you need to think, okay, are there different situations which are very similar, with very subtle differences, so that I can get a notion of the uncertainty as it happens in real life, the stochasticity of the whole thing. So yeah, for me that's an open challenge actually. But I think in the first instance, at least what I've been doing agent-based models for about 3 years. The one thing that I would really encourage is for people to think about, okay, when you develop rule sets, let's try not to just minimize the error, because that can lead to all sorts of biases, but perhaps look at the sensitivity and see if we can use that to make more rigorous models and perhaps also a bit more general applicable models. So I'm not sure if that pushes things in the right direction, but it's an attempt.
That's a really handy comment. I would just say back, but one of the difficulties is forming those rule sets, and how do we quantify the uncertainty in the rule sets that we've put together? Isn't the challenge as well? Do you want to fling it over to...
Are you ready?
Or would you prefer a microphone?
Thank you. So, is it still working? Yeah, it is. So I keep in. So coming back to this statistical description, what is the output of your model? Are you looking at densities of people? Is your aim to follow individuals and you want to predict where they go? Because that will very much determine the answer to the questions that you just raised.
The answer to that question, it's entirely dependent. It might be.
Of course, so you have to specify.
We're looking at how many sensors we have to put in a train station to capture information about people to know where they're going, because you can't simulate an entire city.
Of course not.
So it works on multiple scales, multiple levels as well. But I guess my question is there anything that the people who work not in the urban social sciences have seen from our problems?
Well, again, a colleague of mine, Dr. Mike Lees, is also working on these kinds of systems. He has developed quite interesting ways to extract rules for the agent-based systems given data. They have applied this to huge crowds, to the Kumbh Mela in India. So that could be one way to go, but then you need to validate this, obviously, et cetera, et cetera. But again, if your quantity of interest, the output of your model is some statistical description of the density as it evolves, for instance, over time, then you have something you can measure and you can build uncertainties on top of that. The discussion we just had, I think, was about the aleatoric uncertainty in your model. But you have other types of uncertainties that you also have to specify. And there are different techniques to try to entangle these things and to understand what this means. But the simple rule about collision avoidance, obviously, you know, it becomes a branching model. And but again, in statistical physics, we understand how we can analyze these things in terms of distributions. So it will be interesting to exploit these kinds of routes. Maybe if you would be able for a simple agent-based model, like Federico Toschi has done to find Fokker-Planck equations, you can actually understand the impact of this aleatoric uncertainty on the output densities. And that would be one way to maybe build understanding of what this means. And then go back to the individual rules. And then you start to build in heterogeneity. The thing becomes extremely complex. And then but you have to start somewhere. So I could imagine starting with not too complex things that are amenable to the statistical physics descriptions and building an understanding. What about the initial conditions, et cetera, et cetera.
That is incredibly helpful. I mean, and we're studying the Turing Institute, so my next question to that is, there seems to be some great leads and things I've seen. How do we go about joining this up?
Well, just invite Mike to the Alan Turing Institute, you know, and start to talk.
Well, I'm gonna pick on Louise in a moment, because I know the Turing do things in reproducibility. She's just behind you. I mean, if we wanted to do some of this, because Onnie mentioned in her presentation, I wrote it down word for word, that she has her work can be applied to other types of simulations. Maybe you weren't thinking of individuals rather than electrons. So how do we go about getting all this? Louise, what would we do?
Yeah, so I know why I'm being... that's loud. So I know why I'm being called on here. So one of the projects that I worked on last year was the Turing Way, which was mentioned briefly at the beginning of this workshop. And part of the Turing Way's sort of philosophy is that joined-up work is brilliant. Like it means that people can share their work, can build on it, even though it's from different domain areas or anything. So one of our big drives is to try and push for reproducibility as the default in everything that we do. So we've put together a handbook for reproducible data science, where we've tried to take a lot of the things that we've found useful. So some of it's from ourselves here at the Turing, so myself and my colleague Sarah working on the project for quite a few months. And we've also had massive contributions from, I think the last count it was over 75 people, some of whom I can see around this room, and people at other universities. And they've all shared what they found most useful for sharing their work, for sharing their code. So some of it's the obvious, like version control, actual methods of saying, here's my code, you can go do what you want with it, have a go with it. And some of it's also about managing data and all kinds of other different aspects of it. So something we're very, very keen on here at the Turing, and we have quite a big community dedicated to bringing people together in that way.
Thank you, Louise. Peter?
Weighing in on that, I'm from UCL, and I see Serge Ias over there, who's also from UCL at the Turing. UCL is a major sort of founding partner, so to speak, of the Turing Institute. So there's no reason why we can't use that as a mechanism for joining some of these things up. I mean, that's, our particular project, I hope you've understood, is about engaging with increasing numbers of people. So, I would be very strongly in favor of trying to do things like that here. Just on the so-called fundamental and basic science that keeps getting alluded to, by the way. So if you want to understand fluids, many people, let's say applied mathematicians and engineers, I love saying this because it's provocative, they've never heard of the atomic theory of matter, but they know the Navier-Stokes equations, and that's all they try to solve. But those of us who understand with Boltzmann that there's something underneath it realize that at times those molecules, like people, have a habit of screwing up such equations. So there's no guarantee for a complicated mixture, so maybe tomato ketchup or something like that, that it has a hydrodynamic description that's captured by the Navier-Stokes. That doesn't stop the mathematicians and others trying to solve it and shoehorning relationships in that are empirically based to connect the large with the small. But there are better ways of doing that because we can handle what's actually going on at the micro level and then feeding it into the macro. And this is then a kind of multi-scale model that's enabling you to correct the level of approximation of the continuum, But the continuum level in our schemes can often be much more computationally tractable. And you can probably understand for the cases in plasma physics and many of the things I'm concerned with, they are high-performance computing applications. So we want to sort of minimize the compute cost, use the simplest model wherever you can, but feed in more realistic data where it's necessary and try and control the uncertainties when you do that.
Thank you. Serge, do you want to make one last comment for our lunch?
Oh, okay, so very short. I'm very optimistic about the data assimilation, not only because we have a project together, but you made the point very clearly that particle filters are going to be improved in order to deliver. On uncertainty quantification for these kind of models where you have agents that have different rules, I mean strata of agents that have different rules, and in order to be realistic, I'm a bit more concerned. And we need an effort, a long-term effort, I think, across statisticians, computer scientists, RSCs, field specialists. And I wonder if Peter Challoner has some ideas, because Peter has worked on stochastic models. But maybe for lunch, I don't know.
It's okay, we've got time.
I think the methods we've got will work if you're prepared to pretend you're in a continuum and you're working with averages and variances and things. But we're not exploiting the agentness of agent-based models. We're pretending they're continuum models and it works, but that doesn't actually get you what you want, I don't think. I mean, it gets you part way, but I think we do need new methods to dig into the agentness and to work with not just parameters and boundary conditions, but with rules and sensitivity to rules and calibrating rules and doing that in this non-continuum way, which I think is going to be great fun. I have to say, we should do it, but we can't do it now. I mean, I can't this afternoon sit down with you and do that. But I could do it on the continuum. If you're prepared to pretend it's a continuum, we can do that. So we can get part way. But there's a push, I think, on the maths and the stats to build that, go that extra distance. And I think it's the obvious next place to go. So I have no problem with that.
Thank you. I mean, that sounds like a great place to finish. Nick and I and Derek, 3 agent-based modelers here, if you want some difficult problems to apply your methods to, please come and find us over lunch. I'd like to thank all the speakers this morning, Dan, Anna, Onnie and Nick, for 4 fantastic talks. We will be back here after lunch. Lunch is in the Lovelace room.
Yes.
Peter, do you want to say anything else? Everyone.
I'll just comment that we know who wants to go to which of the so-called parallel sessions that are starting after lunch. When does lunch end? I've already forgotten. Is it 1:30? So we will break, have an hour and 5 minutes to chat and so on. At 1:30, if you're into what's called the reproducibility session, it's held in this room. And the other group, which is doing the software work, Vecma and Turing products to look at, that's in something called the Augusta room, which is next to the Lovelace room, which is where we're going for lunch right now. Thank you all very much indeed. See you back here.
University of Amsterdam, and I'm quite happy to be here in the Turing Institute. First time for me. I like it already, so I wouldn't mind returning. I'm quite happy to introduce to you Victoria Volodina. I'm practicing. I was asked to tell a little bit about you. So Victoria is an associate here at the Turing Institute, and you're from Exeter University. And you work on developing practical tools to support government policy and decision-making under uncertainty, which I believe is an extremely interesting and also exciting topic, because I truly don't understand how people decide things. And that will be interesting to get our hands across that as well. But probably you will not discuss that. So please, go ahead.
Okay, thank you for this fancy introduction. But today I'm going to talk more about Gaussian process simulation history matching. So this is the content of my talk. So when we talk about uncertainty quantification, we mostly talk about computer models, and computer models are widely used across the range of field to study and understand some physical processes of interest. So for instance, climate models are used to study and understand current and the future state of the climate. And these models are really important because we use them for predictions and forecasting. But prior to making any inferences based on this model, we should acknowledge and take into account for the major sources of uncertainty. And the main sources of uncertainty that I'm going to talk about are parameter uncertainty, model discrepancy, and code uncertainty. There is a typo. So parameter uncertainty is related to the idea that computer model depends on a number of unknown input parameter values. Model discrepancy, another major source of uncertainty, is related to the idea that computer model is not the ideal representation of some real world process. And the final major source of uncertainty that we're going to talk about is code uncertainty. And it's relevant to the notion that we cannot run computer model at as many input settings as we want, and most of the time we treat it as a black box model. So in computer experiment literature, when we talk about computer models, we define them as a mathematical function f that takes some inputs x, that could be a vector, for example, and provides some output f of x. To study the relationship between computer model inputs and outputs, we want to run this computer model at as many input settings as we can. But most of the time, this is infeasible. So to approximate this computer model behavior across the input space, we need to build a surrogate. There are a lot of different types of surrogates, and we heard about some of them today, such as polynomial chaos, neural networks, and splines. But in my talk, I will focus on Gaussian process simulators. Gaussian process simulators is a special type of surrogate, since it produces prediction, but also produces a level of uncertainty about this prediction. As I said before, we built a statistical framework, statistical model for our f of x, and we specified as a sum of two processes. I can do this. As a sum of two processes. The first term represents the global trend, the global behavior of computer model across the input space, whereas the second term is a residual term, and it represents the local deviation from this global trend. And we define it as a zero-mean Gaussian process with some pre-specified covariance structure. Based on this model, we can specify a prior for our f of x, which is a Gaussian process with the following expectation and covariance structure. And as an analyst statistician, we can specify its regression function, which is h of x, as well as the correlation function r. But we need to estimate the parameters of our Gaussian process emulator. So for these purposes, we collect some training data, we sample in the input space some design points, and we run this computer model at these chosen design points, f. And we perform Bayesian updating to update our belief about computer model behavior in the input space. So this really simple 1D example. We have one input and one output. We assume that we only observed our computer model at these 4 input settings. And we construct Gaussian process emulator that looks like this. So red line represents the prediction from Gaussian process emulator, the mean functions that go through these 4 design points. And on the top of these predictions, we have some level of uncertainty automatically produced by our Gaussian process emulator, plus or minus 2 standard deviations, these dashed gray lines. As you can see, when we move further away from this training data, from these design points, our uncertainty about prediction increases. Here's another simple toy model that will be used to demonstrate the properties of history matching later in the talk. So this is just a simple 2D function, a semi-sphere centered at 0 with radius 1. And we constructed 2 emulators, one using 8 design points and another using just 10 design points. And as you can see, our predictions improves when we use more design points, as we expect. And it's also indicated by a root mean square error metric. As I said before, when we use Gaussian process emulator, we automatically produce uncertainty about our predictions. And here is demonstrated with these 2 predictive standard deviation plots over the input space. So you can notice that when we move closer to the design points, these black dots, our uncertainty about prediction decreases, indicated by this yellow and white regions. But as we move further away from these design points, our uncertainty increases, indicated by these red regions. Also, as you notice, when we have more design points, the level of uncertainty decreases. We have lower values of predicted standard deviation produced by our Gaussian process emulator. And now I'm going to talk about history matching. So today we talked about the importance of computer model representing some real physical process of interest. And in some cases, we could have some observation or historical data, which is termed by Zs. We want to build a statistical framework, statistical model between this observation Z and computer model f of x. And you can see that we also need to include some major sources of uncertainty represented by a model error, model discrepancy that represents that this model is not the ideal representation of real world. And for this model discrepancy term, we define the variance of model discrepancy. We also assume that we collected this observation Z with some level of error. And for this observation error term, we also have to define the variance of observation error. So now we're going to talk about a calibration problem. So we want to find some input settings X for which computer model output matches this observation Z. But we also want to take into account these major sources of uncertainty. So the history matching has an idea that we want to find a set of these input parameters for which this computer model output is close to this observation Z. And for this purpose, we use a distance function called implausibility function that you can see here. But we talk about complex computer models, so we cannot run this computer model at all the input settings. So instead, we propose to use emulator. And our emulator has this prediction, expectation, and variance term inside our implausibility function. So the idea is that we construct an emulator, we compute implausibility function at as many input settings as we can across the input space, and then we want to retain only input space for which this implausibility function is less than some threshold A. And this new retained input space is called not ruled out yet space. So on this simple 2D function that I showed before, we have this input parameter plots. We constructed an emulator using these 10 black design points, and we computed an implausibility function across the input space. And we managed to obtain this Android space in gray, which is 56.9% of the original input space. since we're dealing with a really simple mathematical function, we can also find what the true N-Roy space is. And the true N-Roy space is simply found by using, instead of expectation, directly f of x and specifying variance of f of x at 0, because we're directly dealing with a mathematical function. And this true N-Roy space is this green area, and the size of this true N-Roy space is 5.4%. We believe that, in general, this process of obtaining this first N-Roy space is called wave 1. And refocusing is a process of repeating this process multiple times. So the idea is that if you want to obtain wave k of N-Roy space, you start at the wave k minus 1 N-Roy space, you sample your input space to obtain more training data, update your emulator, compute implausibility function across this input space, and shrink it further down. And we performed wave 2 of N-Roy space on this simple 2D function. We sampled wave 1 N-Roy space to obtain these blue design points. We reconstructed our emulator. We again computed implausibility function, but only at this wave 1 N-Roy space, and we further shrink down the input space. And we obtained this wave 2 N-Roy space, which is 5.23%, and this gray region. The size is really similar to true N-Roy space, and also the shape resembles the true N-Roy spaces you can see from the plot. So with Gaussian process simulators, we are not only dealing with simple 1D, 2D problems, we also have some real-world application. So for instance, in climate modeling, they are interested in this particular application, they're interested to introduce new input parameters that would represent some cloud behavior inside their computer model, but they are really unsure what these input parameter values should be. They have some observation, so they decided to use emulation and history matching to find this set of input parameter settings for which their computer model will match this observation data. So on the left, you can see this diagnostic plot. So they decided to introduce these 6 new input parameter values. They collected some design points at which they ran climate model. They constructed an emulator, and this is a diagnostic plot. So in black dots and black error bars represent the predictions plus or minus 2 standard deviation on these predictions. Green points represent the climate model output. And they are trying to history match to some observation with the error on the top of which represented by these blue dashed lines. They performed history matching, and after performing history matching, they're ready to construct 2D projection plots. So the upper triangle plots represent the proportion of N-Roy space behind each grid box, and the gray regions were completely ruled out, whereas the lower triangle plot represents the minimum plausibility find for each grid box. And after performing 2 waves of history matching, they obtained an N-Roy space of size 4% of original input space. And it indicates the set at which they believe that computer model output is close enough to observation data. So in conclusion, I demonstrated some property of Gaussian process simulation and history matching. The history matching Gaussian process simulation could be extended to multivariate simulators with L different outputs, and we can use for these purposes multivariate form and plausibility function. We can also treat this output sometimes as independent and construct a plausibility for each of them. The refocusing, the whole process of refocusing gives also a number of benefits. For instance, at which a wave we can define a new form of implausibility function, as well as when we perform more waves of history matching, we believe that we're building more accurate emulator because the density of a training data increases over the reduce space, so we have better predictions and lower uncertainty about these predictions. But here's some literature on Gaussian process simulation and history matching in application to climate models, and I think galaxy model as well. But that's it.
We have time for questions. I know there are some GP experts in the room, so come on, guys. Yeah, here we go. That's the risk you're on.
So, when you do the refocusing,
yeah, you have to push the button.
So when you do the refocusing,
That's all.
When you do the refocusing, there's clearly an experimental design issue. Could you just mention some of the issues that that are necessary to do the refocusing? It's not a trivial process.
You mean where should you sample the design points?
Where you sample the points.
Yeah, okay, this is an open research question because after you cut down your input space, this input space is of different geometric shape and of different sizes. So people are struggling with different methodologies. Where would you sample this? Where would you collect your training data? This is part of my PhD. Yeah. Thank you for the question.
There's another question.
Mine is a simple question on the face of it. How many points is enough?
That's not a simple question. So I think a general rule of thumb that 10 points per dimension, but it depends on your model behavior. So issue is that this 10 points per dimension if it behaves stationary, but if you have discontinuities, you should have more points. And this is more question about a design of experiments.
Other questions? Yes, Daan?
So you describe a static situation, right? I didn't see time dependence in what you presented. So I was wondering, can you include that in an obvious way?
So I think my PhD supervisor, he worked with spatial temporal fields. And the idea is that, his idea was, or many other people's ideas, to do some dimension reduction. And then you can construct emulator for each basis coefficient. And then you can perform history matching by building emulator for each basis coefficient and constructing computing implausibility for each of these basis coefficient. But yeah, it's possible.
Also in time?
Yes, also in time, yeah. It's a really flexible tool.
One more question? If not, thanks again.
Thank you.
I'm happy to introduce to you our next speaker, Professor Peter Coveny, who already introduced himself this morning, so I don't need to do that anymore. However, Peter,
you have to speak for a minute because we have to connect another.
Oh, you have to come. Oh, all right, that's interesting. I can tell a joke about Peter, but I won't do that. No, I would say, Peter, you surprised me again because I was reading the title of your lecture in the final program as it was announced on the website, where it said reproducibility and computation. I thought that's interesting.
But now it's
but
much
now
less interesting. You have to
Peter decided. I try to build up the tension. Are we ready? No, that's not. That's mine. No, that's,
I thought we were using your machine. That's why I sent it to you.
Yeah, here you go. So now we're all very eager to learn what the topic of Peter's lecture will be, and I'm trying to stall a little bit more. Those of you who have been following tweets from several projects may already have a hint, and this was work done together with colleagues in the States, if I recall well. Still, you don't know. All right.
Here we go. Look, we have something. Now, it is, so Peter will speak about the limits of computing, which is, of course, you know, one of those topics where we can speak about a lot, and especially in this environment, the Turing Institute, it's of course interesting to speak about the limits of computing. However, you have made that focused a little bit more, and here it is, a new pathology on floating point numbers. So Peter, please.
Thank you very much indeed. I guess this is, can we even work with that now? So I'm interested in finding out how many people here work in areas where the dynamics of your system is chaotic in the technical sense. I know those people who work in turbulence, for example. We saw that in the plasma context, and also climate prediction, for example, fluid dynamics. It's all over the place. So I think I know the people who do that here. What I'm missing typically is this whole community. There's at least as many probably who do this subject as do fluid dynamics, and that's molecular dynamics, classical MD. Who in this room, I met someone in the other room who does classical MD, and it's you. Is there anyone else here who does this? Yeah, Robbie, he's with me, so I know you. What I noticed in a cluster review, so-called in Luxembourg a few weeks ago, which was about this project and others, and uncertainty quantification, is the guy who's now director of the center in Lugano, the computing system in Lugano. Can we remember his name offhand? He's a Swiss chap. He was... No, it's not him. It's the other one. I'm not going to remember his name instantly. Right. However, he pointed out that one of the embarrassing things about addressing uncertainty quantification, for instance, is that it's not uniformly understood or used. And what I've noticed is that while it's grasped and taken deadly seriously in these more macroscopic domains that you might call applied mathematics and engineering, when you get down to the lower levels of these hierarchies, like molecular dynamics, which is still classical, or quantum mechanics below that, the understanding of uncertainty quantification is shamefully small. So there was a discussion earlier in the afternoon in this room where someone was saying to us that we should be honest and point out that a lot of simulation work is not reproducible. And a large amount of that uses molecular dynamics is in that category for reasons that I will be discussing. Essentially, these MD simulations themselves are chaotic, and that's kind of known in the community but not properly taken seriously. So the results of this investigation apply to anyone who's doing molecular dynamics as surely as they do to turbulence and also other areas where chaos appears. And for my money, it's rather surprising that if you understand, as it were, the statistical basis of chaos, you realize that the floating point numbers aren't up to describing it properly. Why is that? Is this going to advance? No advance. So we'll have to go over here. So first of all, quickly, acknowledging the people who collaborated with me on this particular work, as well as a whole bunch of others who work with me, but primarily Bruce Boghossian, a long-standing partner and collaborator of mine at Tufts University, and a PhD student with him called Hongyang Wang, who left academia after picking up his PhD and now works for Facebook. But then briefly, I want to sort of acknowledge funding sources. There are quite a lot of them, and many of them actually are European, so the work is situated in that context. But this is the picture that's of prime concern to us when we talk about chaotic dynamical systems. They exhibit, it's been mentioned before, extreme sensitivity to initial conditions. The slightest change in some initial condition over a long period of time will lead to massive difference in the outcome, which immediately tells you you've got a problem if you want to do long time simulations. This was mentioned earlier. In turbulence, anything which is chaotic and you run for a long time, well, its accuracy will rapidly diminish. And the reason is related to what you don't know that was in the initial condition at the beginning that might inform the long time dynamics. But if you think what goes on in turbulence, the whole statistical theory of thermodynamics is about taking averaging over lots of what we call replicas, ensembles, as is done in things like weather forecasting. But really in molecular dynamics, this is not still recognized as an important thing to do. So people argue that I'll run one simulation, and if I run it for a very long time, that's a good idea. I've just told you it isn't. But even if you ran it for a long time, you're supposed to appeal to something called the ergodic theorem or hypothesis, which tells us that that's the same as the ensemble average, which is actually what you're supposed to be doing, because in these areas, if you want to calculate something useful from molecular dynamics, it's typically a free energy. We're interested in that for a lot of reasons, binding of one molecule into another. That's a macroscopic quantity. It's not a microscopic one. And in the theory of statistical mechanics, you must perform ensemble averages. So it's one and the same thing. You must do it to get your uncertainty under control, and that's the only way you're going to get a free energy. And you claim that if you run it for a long time, you will see the ensemble average, but nobody knows how long it is. In practice, they run for as long as they can be bothered to, or the power of the machine allows them, and then they call it a day and say, well, that's it. But actually, that hypothesis only holds in the limit where t goes to infinity. And if you think about it, it requires you to enjoy what we call a Poincare recurrence, which is where the initial trajectory has gone through every possible point compatible, let's say, with the energy. And we all know that's an astronomical number anyway. And the interesting thing, if you think that I'm working at two levels here conceptually, one is the trajectory, where I'm supposed to know the initial condition exactly, but macroscopically, the concept of equilibrium, in which free energy exists, is one where there's no dependence of the system on time. And that's because we're working at another level, which is the probabilistic representation. At the level of the probability distribution, where you might have started, this system, if it's going to display an approach to equilibrium, must have specific ergodic properties which are never discussed in textbooks or lectures. And that means they must have this chaotic property. Specifically, they've got to have a property called mixing. I'm not going to go into it, but that's what then leads asymptotically to the system having an approach to equilibrium. And actually, again, without going into the technical detail of that, the condition under which the system reaches equilibrium is something you can only articulate in the measure theory, Lebesgue's theory. And it applies, as they say, almost everywhere, except possibly to a set of zero measure. The floating point numbers are a set of zero measure. I mean, the computable numbers of Turing are a set of zero measure, but the floating point numbers are an even smaller measure, and we have to understand their structure, because that's what underlies the weakness of them in being able to capture the exquisite sensitivity of a chaotic dynamical system. So if you have a molecular dynamic system or a turbulent system or something else, you have intrinsic to it this stochasticity, which is due to the instability in the initial condition. And that's important to get on top of before you start worrying about other sources of error, which are usually systematic errors that come from things like the parameterization. What you'd like to do in molecular dynamics is know the distribution function, the equilibrium distribution function. But for any real system people are interested in, they've got no chance in hell of knowing it. There's no analytical representation. So you try to compute the expectation values, and people talk about all kinds of sampling techniques to do this, enhanced sampling and so on. Fundamentally, what's involved, and you'll see us talk about it here, is the requirement to do extensive ensemble and time averaging, and that's what the statistical theory of turbulence is based on. There's no statistical theory of molecular dynamics that I ever find in any textbook, but that's what I'm saying you need to do. So what we want to do is investigate how well a computer, using the floating point numbers, can manage to capture the true behavior and known behavior of a system for which what we call the invariant measure in the jargon of dynamical systems, that just means the equilibrium distribution, is known. There aren't many systems for which that measure is known. They're very simple systems. And this paper is about the one case where we've been able to analyze it. So we know all the results for the equilibrium properties of a particular dynamical system. It's absurdly simple by comparison with all the ones that people use in molecular dynamics. There's only one variable and there's only one parameter. But I'm going to tell you that the floating point numbers can't capture that. And so the question you're going to have to ask yourself after this lecture is, if it doesn't work for the simplest system I can show you, how on earth do you expect it to work for the more complicated ones? Here's the system, Bernoulli map. Originally, all it is take a number in the interval between 0 and 1 and multiply it by 2. And of course, then you take the modulus of the number and the bit that's within 0 and 1 you continue with. That's what makes this map chaotic. And you can't get systems that are much simpler than that. So it's one-dimensional. And the generalization of that is where the parameter beta is replacing 2. And that's the thing we're going to vary. We assume it's an integer or rational number. Of course, we can't capture the irrational numbers on a computer in general. And the point you all know as your good Turing experts is the real numbers have a split between the rational and the irrational numbers. And there are many more irrational numbers than rational ones. So you should be a little worried that you have the cheek to think that the IEEE floating point numbers, which are just dyadic numbers, that means every number can be represented as a number whose denominator is a power of 2. That's supposed to represent all the numbers you may ever encounter. It's a bit of a cheek to think it works. And then after this lecture, you'll be wondering how it does so well with that. So this is the problem. I know a lot about this map. It's been studied over 20, 30 years. And we have the invariant measure, and we can try and calculate that. What we're going to do then is form a floating point representation of this thing and investigate how well we can recapture the known mathematical properties. So what is this thing? Why is it interesting? It's very simple, but it's kind of prototypical. And in the jargon of dynamical systems, it is also topologically conjugate to a lot of other systems, including, for example, the logistic map, which is known in population dynamics and so on, with the certain choices of parameters. So the findings from it immediately extend to quite a lot of other simple dynamical systems. So its exact properties are known. The initial condition is called x0, and that's what the map is. And we can look at different values of beta here. And just summarizing what's known about it, it has a dense attracting set. We know the invariant measure, which is this probability distribution. If you do this thing many times, where will you end up on the interval between 0 and 1? And we can calculate exact expectation values for it. I'll show you some pictures of it in a minute. So the case for integer values of beta greater than or equal to 2, we know that this measure is uniform. It's just like it has a flat. Between the points 0 and 1, it's just uniform across there. Rather boring. It just says that any position in that interval is equally probable. Things become more interesting when beta is non-integer. Actually, much harder to get results there, but there are some known. We have an exact expression for this thing, which is, this is a Heaviside step function, showing you this thing is actually very discontinuous. It's more discontinuous than you can see in these plots. But here's the value of x between 0 and 1, and this is the value of that probability distribution. So it's no longer uniform. It's a bit like you did molecular dynamics with a protein. I know it's only one dimension and one parameter. And depending on where you are in the phase space, this protein thing could be sitting in different conformations. So depending where you are, you've got different probabilities of being in different states. So that's known, and the question is going to be how well can we compute that using the IEEE floating point numbers. Just to remind everyone what they are, we're talking about here single precision, and what I intend to do in this exercise is use every single floating point number that I have available. There are 4 billion, roughly, floating point numbers between minus infinity and plus infinity. So 2 billion are positive, and 1 billion of them sit between 0 and 1. You just have another billion to cover everything else. They're very non-uniformly distributed because they're dyadic numbers. So that's also a bit of a worry. But anyway, you should know this basic stuff about floating point numbers. And I will come later to explain about the double precision and other levels of precision here. But we can do this calculation with all the floating point numbers loaded into a reasonably small computer today. You can't do this calculation with the double precision ones because you'd need an exascale machine with a huge amount of memory. So you can do the calculations. The way this works is you look at the unstable periodic orbits of the system, and they present you with the ability to compute the ensemble averages. In a nutshell here, you use something which is known as the Ruel's dynamical zeta function to calculate this. That's a detailed aspect I'm not going to worry about, but effectively we're using an ensemble averaging over every possible initial condition. We get the system onto the unstable periodic orbits, and then we can average over essentially infinite time. This is the best we can do with any floating point calculation. And that's what we have to work with. You couldn't do this calculation more specifically. What happens? If you can consider the case beta equals 2, actually this case is really pathological because then you're representing the position in terms of binary bits as a bit string. So the overwhelming probability of initial condition is irrational, and that's just going on forever. But we don't have irrational numbers here. We have the IEEE floating point numbers with a few the number of points after the decimal in the binary thing here, I should say, in the binary expansion is 23. So if you keep iterating this thing after 23 iterations, the result is 0. And if you did it with a double precision, you just take longer to get the same result. So actually, without going any further, you just find that the end result is the computer predicts that the expectation value is at 0, x equals 0, whereas I told you the analytical result is uniform. That's one hell of a bad prediction. It's totally wrong, in fact. What happens when you look at cases which are rational? Things become more complicated. I'm going to run out of time, but you can, in fact, categorize all of the unstable periodic orbits. Just notice that the chaotic trajectories, which you can't capture in the system, are irrational numbers. You have a dense set of these unstable periodic orbits. And the number of orbits you can compute is painfully less than the known total that you can get. It decreases shockingly with the period of the orbits as well. So the structure, the very dynamical structure of this trivial system is completely badly represented by the floating point numbers. Let's see, though, quickly what happens. There's two categories beyond the even numbers. There's the odd case. I'll just tell you that looks like a pretty good agreement. The blue number is the invariant measure from continuum mathematics. The yellow-orange thing is what the computer predicts, and they look to the eye there almost exactly the same. There is an error here, which is 2 orders of magnitude greater than machine precision, but we don't normally worry about it. When we look at the case when beta is non-integer, this is the generic case, and you'll remember that sort of fractal devil's staircase behavior. If you do this calculation with a floating point, now you're looking at the difference between continuum exact and what the best result you can get on a computer is. And that means that if you know the probability distribution, you can calculate the expectation values. These things could be badly wrong significantly. And there are just a few examples of the deviation in this case from exact behavior, which would be there as a fraction of the power of the exponent x if I was calculating x to the q. And in this case, the errors are typically of order unity. They can go up to between 15 and 20%. So that's the best you can do with a computer there. It's also related to the length, the longest unstable periodic orbit you can locate in the system, which is shown here. And this also applies to the case of even x, because the value of that is just exactly 0 for that case. So it's really pathological. So the conclusions from this, since I think I'm running short of time, are the floating point numbers aren't up to the task of representing the structure of these periodic orbits. It's a pathology that you can't get out of by doubling the precision. And the reason for that is, even if you have high precision, they're still dyadic numbers, and the points on most of my unstable periodic orbits are numbers that aren't dyadic. Like period 2 has a point which is 1/3 and 2/3, and the binary expansion of both of those is recurring infinitely. I have to truncate it. I miss the orbit completely. So numerically, I miss the whole thing. So the errors in the generic case are of order unity, and for such a simple system as the beta shift, that's pretty tragic. It's meant to be a model system. Higher precision won't rescue the situation. And here's the issue that matters to the practitioners who are launching their simulations, apparently blissfully unaware of this issue. If it's the case for such a simple system as this, there's no reason to think it's going to go away when we deal with simulations of far greater complexity. The question is left open for me and you to find out what the scale of the errors in those calculations that you just assumed were correct because you put them on a computer, what the true deviation of those is. I put it to you that that's a fundamental component of uncertainty quantification in these problems. With that, I shall stop and thank you for your attention.
Food for thought, and I see some first questions already. What's the solution?
Well, the next step, so to speak, when one might try to mitigate these things. Okay, the easy and glib answer is you've done everything you can with the digital hype. Now try analog reality. If I put this on an analog computer, it would give me the right result. I'm quite sure of that. Although the results might change depending on the material on which I did the calculation at some order. But the continuum solution is going to work. The issue now is on our beloved digital computers, how do we fix this? First of all, there will be people who take no notice of it because you have to be able to show you've got an error here. So we have to look, for example, at other systems and display the errors there. And we don't go straight to molecular dynamics. We look at the Lorentz equations that Dan described earlier, because we've actually earlier, 10 years ago, calculated the UPO approach to evaluating expectation values there versus regular time interval. There are a lot of differences. It all remains to be investigated.
FPGAs. You don't actually, we mentioned IEEE 754, but you don't actually have to have this particular form of floating point that largely was invented by IBM in the 1960s.
Yeah.
You know, I remember the 60s, even though I was there. But you know, the things you cited are because we've taken the cheap example. You know, a cheap processor we can buy on Tottenham Court Road still, just.
Yes.
So are you saying that we need to change our hardware?
It's not so necessarily the hardware, it's the number system. One way we could ameliorate this if we had a numerical system that could handle rational arithmetic. What we're doing is dyadic arithmetic. It's closed under multiplication and addition, so it's a nice, simple system. So we could look at alternative number systems. One of them is promoted by John Gustafson, and it's called unims and posits. But the posits are all dyadic numbers as well, and the unims are intervals. This map has expanding intervals, so you're not going to solve it that way. His solution, he became interested in this, he now agrees won't work for this problem. We have an open season for those who care about it.
Other questions? So I had one, Peter, when you said let's go on analog computers. The first thing I think, yeah, analog computers are noisy and they're not discrete. Your iterated Bernoulli map, that's also something that is very discrete because of the modulo operator. That will never happen in nature. So if you add these thoughts together, will the problem then go away?
Yeah, there are many ways of trying to mitigate it. I mean, one of the ways...
Okay, fine, mitigation strategy, but so then the true question is, so will it go away because in true natural system it would not happen, or could it be that indeed in molecular dynamics or in molecular systems that we may see these issues of representing nature in a computer?
Yeah.
Whether analog or digital.
Well, it remains an open question, so I'm not going to say what the answer is. They're good issues to look at.
One final question? Yes? I'll bring you the microphone. That's my duty. Here you go.
I understand why you haven't tested this because of the combinatorics, but would it not be rational to posit that increasing the precision would reduce the error?
It won't
eliminate it.
It won't. It won't. All you do is wait longer to get the same wrong result.
Okay.
So it's it's likely to just because it's so dependent on being able to capture these points on the unstable periodic orbits. They control the dynamics of the system, and it doesn't matter if I get the precision going out, twice as long as in the single precision. It's going to miss the accurate representation of a third or 2/3, etc. And it won't matter what radix or anything you use for these systems. You'll always get the same kind of problem.
So Peter, I have one final question before we break for tea. Nobody has mentioned the Q word yet, so what about quantum computers?
Oh yes, that's one attempt by people to try and rescue the embarrassment, but the situation is that quantum computing doesn't really deal with nonlinear systems at all. It's powerful because it's linear and quantum mechanics is linear. In any case, every quantum computer that's being developed, or no, most of them are also digital. They use the same numerical system to report results. So there's no solution from quantum mechanics in that sense. There might be, because people are doing analog quantum computers, just as there are a few people doing analog classical computers, neuromorphic computing. There are people from Manchester who know about that for the Human Brain Project. That feeds into the dreaded Roger Penrose argument about artificial intelligence on digital computers will never emulate human thought because it can't solve these kind of problems like Gödelian decidability or undecidability. There are some problems that a computer you have to face cannot solve, and that's the issue for us to consider.
Thank you, Peter. Thank you again. So let me check, because in this session there was a third issue scheduled, namely a discussion, but we started a bit late and it's almost coffee tea time, okay. So we might as well break and discuss while enjoying a coffee and tea, right? So let's do that. So we'll see you again when? In half an hour from now, I guess.
Half an hour from now?
Somebody should
He's going to check. He's checking. At 4 o'clock, apparently.
At 4 o'clock. So in 15 minutes, then we're supposed to be back here for a panel discussion.
Coffee this time.
I don't know.
Coffee?
No, there wasn't coffee.
amount of time. We need to finish by 5. This is a panel discussion, and of course it must involve the audience as well. We don't want talking heads, the same people saying the same things. But I think it would be quite handy for a quick catch-up on these 2 parallel sessions during the afternoon, since some people clearly were at one but not the other. And Derek is was one of the guys with Eric Daub on the software kind of efforts, and it'd be great if you could summarize how that went.
Yeah, so we did a hands-on tutorial with an earthquake fault simulator called FDefaults, and we coupled that basically with a Gaussian process emulator called MOGP. And what we basically did is, given the data, what kind of parameters, input parameters would we need for our earthquake simulation, and what range of input parameters would be viable for that. So we had a practical hands-on exercise where people would run this simulation for different parameters and then train Gaussian processors, kind of a surrogate model, and then run that and basically generate results over, okay, what are the parameter ranges that are feasible and which ones aren't. This was all on the local host because we can't instantly conjure a supercomputer, and people have different access rights. But the good news, I guess, was that as far as I could tell, the majority of people got it working. There were a couple of people who were sort of struggling to download the 800 MB Docker image over Eduroam that sometimes provided speeds of about 700 kilobytes per second. But other than that, I think things have been relatively smoothly. So yeah, overall, I think it went pretty well. Of course, I'm biased, but yeah, so I think it was pretty good.
And what about convergence of software tools and so on? When I say convergence, from, let's say, this Vecma project with what's going on in the Turing. Your work did combine bits of both.
I guess, so I'm technical manager in the Vecma project, and my big fear is always to get this enormous tower of software stackery, and then the project completes and everything falls over like a house of cards. So within Vecma, I've been strongly pushing for the tube map approach, where every piece of software is a station, and every application is a line, and it might use one tool or 2 tools or all the tools. So in this case, we tried to showcase that. So in this case, we used the FabSim automation toolkit from the Vecma toolkit. But then we used some Turing software, like the MOGP Gaussian process emulator. And we sort of put that together. How long did it take us to make the tutorial? A few days? Yeah, I think 2 weeks ago we had the first discussion. So it's yeah, it's not ultra easy, but it was quite doable. We did a lot of other things in the meantime as well. So yeah, today it worked. It's still online, so if people want to do the tutorial later on, we'll share the URL by email, I think.
I'm hoping to find ways in which we can continue to work together into the future. So that's what I'm looking at.
I think we have a strong intention to do so.
That's good to hear. So I also got Marco Verdicchio here, showing that we don't only talk to the panelists from the off. Marco, amazingly, he stood for an hour and 15 minutes leading the discussion on reproducibility, and I did draft him in that at less notice than you did for producing your software. Can you just summarize what came out of that and some of the stuff on that slide?
So in the reproducibility parallel session, we had an hour discussion on several points around the concept of reproducibility. The main questions are shown now in the slide we went through. Let's say the main topic we discussed through were tools and new technology that can be helpful for reproducibility, and this connect very well with your parallel with your other session. So which container technology should I use? What are the limitations of this technology for the workflow you're actually running? And then there was actually quite active discussion on what reproducible means for different people, different audience. And I'm working in a HPC center. For us, is a lot based on outdoor utilization, so different hardware can produce the similar results. But there were different point of view, so really the concept of what reproducible means in the different aspect of research. And then also a nice discussion around the topic of fair software coupled to fair data, so the principles of funding interoperable, accessible and reproducible, applied to softwares, and also how these can change actually the mindset of researchers, not anymore only focusing on publishing their data, but publishing reproducible data and sharing not only the results, but also softwares and all the procedure used. And I think this.
And can you just mention the ACM initiative?
Yes, so also ACM is very interesting in this field of new environment, new journal, let's say, to publish actually more software-related material together with environment to correctly publish the software and data-driven research, let's say. And this is also in all these aspects, a new field of machine learning and deep learning. We actually also discuss a bit also the consequence of applying uncertainty quantification and on machine learning and deep learning. And ACM also very interested in this kind of new way of publishing, new way of disseminating your research. If I
so great, and there's an opportunity for us collectively to interact with them. As I said in that session, the people there are trying to build an initiative, and they're looking over here to see what we're doing, and collectively we have an opportunity to interact with them. At the beginning of the day, I mentioned the Turing way, and you over here have things to say about it. And I think you should just quickly remind us of what's happening there and what effect it's having on maybe the younger generation of people now, because not everyone was listening to what you said earlier.
About the Turing way,
yes. Well,
so
what is the Turing way? Just make sure people, because it's sometimes referred to as a book, but it's virtual.
it is a virtual book, yeah. So it's a Jupyter book, actually. So this is sort of where the Jupyter team have taken Jupyter notebooks and made a format where you can easily set up code and text and have it interactive if you want. So the entire book is based around this. We write the files, and it all gets pulled together by continuous integration to give this wonderful interactive book. So I've had contributions from a range of people so far. A lot of them have come from students and early career researchers. We've held several events, which we call book dashes. So these are like one-day events where we encourage people to come together and generate content for the book. And then we also held a really successful day at the Collaborations Workshop run by the Software Sustainability Institute last year. So yeah, we're actually growing now. So we originally in our first year, we were just about reproducibility and data science, because that's obviously a really huge issue for lots of people. But we now realise that a lot of people want to contribute things that aren't necessarily about reproducibility, but are still about best practices in what we do. So we're now expanding to cover ethics. Reproducibility is still a very big thing. Project design and how to collaborate. And then there'll be also one book that draws everything together and sort of pulls in all the different strands of the Turing way. So we're still entirely open for contributors. If you just search for the Turing way on Google, you will probably find our GitHub repository and all the links to all the other resources that we've got out there. So yeah, please do take a look and feed in with whatever you will find helpful.
Very good. And unfortunately, a person called Laura Fortunato, who's at Oxford, wasn't able to come here, and you, Dominic, were willing to sit there in place of her. You were contributing quite actively to the conversations and pointing out how difficult it was to get the same results with different pieces of hardware and so on. What's your take on what you've seen here today?
I suppose what's interesting, of course, is we're looking at the entire stack from silicon back to how we actually organise the projects. And I think, I'd like to ask, because we're dealing with a sort of mostly relatively young audience, how many people here have actually had formal training in how to build good software for their projects, rather like the Turing way or like that? Right, that's...
The younger ones.
The younger ones. So it's well, no, I mean, that's it. And I think I remember at one point someone disagreeing with one of the points I was saying was only computer programming, and I wasn't at all offended by that, even slightly, even though I am only a computer programmer. I would be interested to see how we can develop better testing for these things. Trying to refute our own results. I have a background in software quality, getting large programs, sometimes very badly written programs, this sort of kind of work. And without some sort of adversarial approach, which is the current buzzword in AI, if we have systems and they produce results and they seem plausible, I think that there needs to be an extra addition to perhaps the Turing way, which is that we actively try to break the system, which is how in bog standard computer programming, something we've now been doing for 30 years. And I fear it hasn't quite really got into scientific computing, where we're actively trying to break these things. Part of my work involves some number crunching, some of which controls really relatively large amounts of money. And I'd never get away with some of those things, you know, code reviews and, you know, oh, it seems to work. We need to have some proper quality metrics. Yeah, at the back.
Hello?
Yes.
You can hear me. Oh. Well, I wonder if there's such a thing as a catalog of what computer software or computational tools, a catalog of what their purpose is in science. Does that exist? I mean, there are signal detectors, there are modelers. You know, if you take the chain data to publication, yeah, or hypothesis, data, publication. So you have instruments, you have data collectors, you have humans, you have theories. Software is, I mean, I can see, you know, I can think of some roles. What is the science of that? Because I think you will have different quality control criteria for different types of roles.
So let's ask Onnie what she has to think about that. You're working with this incredibly complicated tier, multi-tier. I can't remember, it's got actually 9 levels of representing different scales of modeling, etc., which is eventually meant to be integrated. That's complicated enough. How do you handle that as a community, let's say in plasma physics globally?
Right now, we're trying to take it one step at a time. So the model I showed you, it's a much simpler model, and we want to understand that and what happens in the core of the plasma before we study, for example, the plasma interaction with the wall of the tokamak, which is very important as well. So there's another, you know, like branch of physicists studying that. But yeah, I don't know if I have a good answer to.
But is this a global effort, or do you regard yourselves, say, as competing with the US with your codes and software? Is everyone working together? The Large Hadron Collider particle physics is sort of globalized now.
Right.
Is fusion research in that category, or is it more fragmented?
I would say yes, especially when it comes to ITER. It's a big collaboration with seven different partners: EU, China, Japan, Korea, India, US, and I think Canada. I'm losing count, but anyway, there are a lot of scientists working towards that. But then there's also competition as well, because you know, there's so many people with like similar models, but then they claim that they can do better than the others. And so there's this competition, or, you know, this competitive like mindset as well, to see who can get there faster, who can provide more. And a lot of times I realize that turbulence, or even like kinetic codes, people claim that it can do so many things. But is it really true? And, you know, like, do people sell their model? That's something that I thought about as well when it comes to reproducibility. Like, people claim certain things, people tend to sell it in a really beautiful way, but, you know, is it really working? And then also, like, codes become, like, some of the bigger codes have a lot of people using it. But is there anyone actually going back and check whether the implementations of, you know, different scientists adding into the code, are they correct? You know, little things like that I feel like my community may not be doing the best possible. I don't know about the particle physics side.
I think there may be 1 or 2 people still in the room who work with UK AEA, which is the Atomic Energy Authority. Are they here? And there you are, right. So Rob Akers, who I know well, was very keen for you to get involved, but I'd like you to, indeed, tell us a little bit about a pretty big initiative that's sort of surfacing in the academic sector, but has been talked about in government circles with some companies in UKAA. It's got this acronym of Excalibur around efforts to take actually UK to exascale and so on. And how do you're in sort of fusion research as well. How do you see the world from your perspective?
So for Excalibur, it's a kind of a project that we're involved in with the Met Office to, as you say, like look at computing towards the exascale and its possible applications in climate and also fusion. But there's scope for people in other areas to make bids related to that as well. From our side, I think we've also got a project to look at building a new boundary turbulence code, and I think a lot of the work that we do will be related to that, looking at scaled down variants of that problem, seeing how, like, comparing different algorithms and looking at how they scale onto larger numbers of cores and heterogeneous architectures and things like that. So like, I think Rob's interested in like mini apps and things like that. So I think it's still like a very new project. We only had like the kickoff meeting for this just before Christmas, so it's still kind of finding its feet a lot. But yeah, I think it should be quite exciting.
Right. So the UK academics have started to hear about that more recently with a call where there were people trying to scrabble for what currently is a bit embarrassingly small sums of money as a first step to potentially doing bigger things in the UK sector. Yeah?
Yeah.
And so now, Alphonse, I think it was you, I may have mentioned it as well, when we do things in the biomedical area, which is about potentially being able to predict things, the actionable scenarios that I was conjuring up right at the beginning, how are we going to be able to interact with agencies like FDA and EMA to make sure that all the science and research we're doing is actually going to be taken seriously by these people? Derek, hand that on.
Thank you. Is it on? Yeah. So, maybe first one step back, Peter, because I keep listening and thinking like maybe a few comments. In computational science, the first thing we do is building models. So they represent reality. Could be a mouse. Yeah? In our case, these are typically mathematical models. And so they represent reality in some way. And if we ask the model a question, it should be close enough to reality, and then we call it valid. Right? So we have to not only write down a model, but also the question we want to ask to the model, the context of use. FDA, that you mentioned, finds this an extremely important thing. We tend to forget that. So we have a model and context of use, and then we can find out to what extent it is a good enough representation of reality, and this is validation. We need to do that. Second, since our models are mathematical models, and typically we cannot solve them analytically, we have to solve them on a computer. This is where verification comes in. And typically we do this by numerical discretization, so we have to ask ourselves the question, is the numerical scheme well enough representing the original equations? And then we have to put the whole thing in software, and this is where software verification comes in. And then we may even ask ourselves the questions, and what is the influence of the digital representation of the real numbers and everything that happens when we do minus LM or something like this in our compiler. We have to be very meticulous on these things. Otherwise, this is an ongoing discussion, and it's going to be more a semantic discussion than something that really helps us forward. Then back to the medical domain. So yes, we are trying to build in silico models of pathophysiology, so health and disease, and we believe that these models or the simulations that we want to do with it can actually become primary evidence in certification of new medical products or new treatments or new drugs. And with primary evidence, the FDA means that it could replace animal studies or studies in humans. Now, in order to be able to have this accreditation that a model and the implementation of the model is a source of primary evidence, we need to go to a very meticulous VVUQ procedure, which is of course based on very solid engineering principles, let's face it. So our friends in the engineering sciences know pretty well what is meant with VVUQ. Now, this is written down in a standard, and currently we actually see in silico models in this biomedical domain reaching these states of fully accredited by FDA. Of course, here in Europe, we're running behind big time. The European Medicines Agency is still trying to understand what this fully means. And the European landscape doesn't really help in that respect. But I think workshops like this and feeding this into the European Medicines Agency will be quite helpful. I'll stop here. I can keep talking for hours, but let's not do that.
We mustn't do that. Now, Peter Challoner, I'm interested in your take on what you've seen today. As someone who's coming at all of this as a kind of mathematician, where the big issues are and remain, or the ones that we should be going for first.
Okay, well, I'll start with how I got...
Is that switched on? Just check. Push the button so it's not a light. Yeah.
So I'll start with how I got interested in this, because I used to be an oceanographer a long time ago, and someone put up a plot, and it had the model, which was just a straight line, and it had the data, which had these big error estimates on it. And I thought, why doesn't the model have the error estimates on it? And I think that's the crucial thing that I want to do. I want to put the error estimates on the model in the same way that you cannot publish an observation or a lab-based experiment without error estimates. I don't think we should publish model results without error estimates. And when we compare them, we should use those error estimates to compare. So if you take the climate projections, there are about 20 plus models that make those climate predictions. None of them, as far as I know, have error estimates on them. It's one of my great failures. I've been getting on for 10 years to try and get to do this, but they don't. Because it's expensive and difficult and whatever. They've got other things to do. But you can't tell whether they're the same or not. They all predict approximately the same thing, but are they really predicting the same thing? If we had the error estimate, could we see that they are the same thing? So I see my mission in life is to produce methods to enable you to do that. And I'm evangelical to go around to tell people you should do that. And if anyone wants me to come and talk and give that talk, I will. Because that's the standard we require of people in laboratories, and we have for the last 100 years or so. And we don't live up to that standard at the moment. Computational people don't live up to that standard. We don't produce error estimates. We don't say, this is my estimate of X, and it could be this, and it could be this. We just say, this is my estimate of X. And that's really hard for decision makers. If someone wants to make a decision, and they've got some empirical evidence which has got error estimates on it, and they've got a model, numerical model output without, how do they balance those two together? It's a great failing, and I know why it's a great failing, because it's hard, but it's getting easier, and we have to keep making it easier and get it so people do it routinely.
I wanted Dan's view on that as well, since it's a climate issue.
Yeah, I was wondering how you feel about how sure are we, even if you can put error estimates, or you try to put error estimates, in particular in the climate context, there being say experimental results with sample size 1, effectively, right? It's the current climate. Just one realization. So is it even possible to really quantify the total uncertainty? How sure should we be about those estimates? Right, so the error of the error estimate.
Okay, so yeah, we only have one planet. It's an observational study. But other people in observational studies manage to put error estimates on things. And a lot of the error estimates in the climate models are about the numerics, not about the data. I mean, I'm a Bayesian statistician. I'm quite happy to take expert opinion. And if you're taking expert opinion, you should probably take a few experts and get a spread. And yeah, I think you might have to put on broaden the, I wouldn't say uncertainty on the uncertainties, because I think that lies madness, but broaden the uncertainty because we're not sure about other things. And we don't know what certain parameters are, and we never will know, because, as you say, we only have one planet. But I still think we can do it. It makes the uncertainty a bit broader. And the uncertainty has to be traceable, and that's part of the reproducibility. that if you use expert opinion, you should say this is Joe Bloggs' expert opinion, and they stand by it, but you could have a different one, and that's fine, as long as you are an expert, as long as you're not just some guy. And things have to be traceable and reproducible, and other people, then we can have an argument. Then we can actually have a sensible discussion. You can't have a sensible discussion if you don't put down what your uncertainties are, if you don't put down how you got there, if someone can't read your code. We just can't have that discussion, and we must have those discussions, because people are using this to make real decisions about people's lives and millions of pounds.
So I think there's still a role for expert opinions even in the climate domain. I mean, we know a lot about the physics. It's just putting it all together. It's very difficult. So you think experts' opinions are still relevant there?
Yeah. So if you work in climate, I used to work in oceanographers, say, and in the climate model there will be a parameter that's called ocean viscosity. And if you go out and measure ocean viscosity, it's something that's 10 to the 6 different. And that's because that's a numerical viscosity in the computer model to do with the discretization and the way that Navier-Stokes works. You can never go out and measure that. You're going to have to either calibrate it by fitting it to data, or you're going to have to work with expert opinion. You're going to have to say to the people that build the models, what numbers work? And I think you should start with that, and then you should calibrate it, but calibration is hard. And there may be some parameters it's really hard to calibrate. So I think there is a role for expert opinion. I wish there was. In some ways, I wish there wasn't. I wish we could just make everything very objective, but it's not. The world's not like that, unfortunately.
Derek, now coming to you in terms of the interactions that occurred during this meeting on agent-based modeling, can you give us a view on what the meeting has achieved from your perspective, and also our colleagues from Leeds who did have to leave early because they won't get home if they waited to the end. So you're sort of speaking for them as well.
Okay, well, that's a big responsibility, but I'll give it a shot. I think one key thing that was very interesting with the presentations from Leeds earlier today and the work that's done in my own group is the very different ways in which we look at sensitivity of the models and uncertainty. In a way, they looked at the outputs of the model and then, for example, using particle filters to create circuit models. Whereas within my group, we're operating at completely the other end of the spectrum of simulation building. So the thing we're most uncertain about is in a way not even the outputs, because at least we have validation data, but it is what we put in the simulation. So what is the logic in an individual person? And that gets really, really uncertain, not only in the sense like, for example, I am a person, I'm in an area of conflict, I have to flee. How much more likely am I going to go to a place that is twice as close by as another place? But even to the point as in, is the distinction with the distance variation, is that going to be a binary thing, a bimodal thing, a sudden thing, or is there a gradual change between these things? And there's a lot of very basic aspects of human decision making that we are uncertain about. So when it comes to quantifying that, or even just finding out the sensitivities, that's an enormous task that is ahead of us. And the key is not so much what is the ideal rule set. That will take a long time and a lot of research. I think the key is what can guide us in the development of that rule set. And I think that's one reason why I got increasing appreciation of sensitivity analysis, because it can provide us, if we have a rule set which is clearly not good, at least by validating the quantities of interest and perhaps also other quantities that are not directly interesting for our paper but still are important to match. And to see how sensitive those quantities are to our input parameters, we can start to figure out, okay, wait, these aspects of our simulation are perhaps not refined enough. And indeed, perhaps instead of taking a single parameter, we need to derive it from data and do the hard thing on that particular aspect. And I think what I find really interesting and also important is you have the uncertainty quantification, the sensitivity analysis. And I know in some disciplines that the laws are set in stone and it's all probably fairly straightforward to put together. But I think in our case, the most important role for uncertainty quantification, also verification and validation, is as part of the simulation development process to work towards a more realistic rule set of our simulation.
Thanks, and I think there is every opportunity for more interactions with the guys from Leeds, because they kept prevailing on me and maybe you. They run an urban analytics workshop maybe every month or so, and they're looking to interact more with you. Alphonse, you want to add in something?
You know, again, so what I noticed in this discussion on the agent-based models also is that if you ask, yes, but what do you want to get out of your models? This is not well articulated. We want to do UQ on agent-based models. That doesn't mean anything. So it has to be much, much more specific. And then you can do this job. You know, if you want to build it, of course, I also talked to the people from Leeds, and then I said, hey, the city simulator. Said, yeah, you know, that sounds good, but it has to be much more specific. And then we're getting somewhere. And again, you know, on these agent-based models, I don't believe you're going to actually simulate paths of individuals. It's always going to be a statistical average. You're going to look at densities, you're going to look at probabilities, and then you have a quite different question in terms of validation and UQ. It's also like modeling on the population level or individual-based medicine. We know that you have quite different questions to ask and to care about.
But anyway, they discovered there's a lot of data on cities like Amsterdam,
a lot.
and active people in the computational science lab at the Institute for Informatics, which you're now the director of, in Amsterdam. That was good. So it is really important for other people to tell us what they think or raise questions before we finish. Yeah, use that one.
Just a comment, drawing on a few things that have come up. I know Peter mentioned that his crusade has been to get people to put error estimates on that. And something that always struck me coming out of having worked on the Turing Way, one of the philosophical goals of that is to make reproducibility too easy not to do. You want to make it so that making your work reproducible actually makes your life easier, and then everyone will do it. If just to get your paper published, you need to publish your code, you need to make it possible for people to look at your results. You will not be bickering with reviewers over such and such did this right and such. You can say, this is what I did, and you can verify that happened. You know, one thing that's come to me working with Derek the last 2 weeks is that a lot of things that I struggled with running a lot of HPC jobs, there's actually a tool that makes my life easier and that solves a lot of the headaches that I had with that. And now I'm totally converted, saying this makes my life easier to do the right thing. And I think a lot of these questions, developing tools that make it easier to do the right thing is going to be an important thing as a community we should embrace and promote.
Great. There's a question at the back or a point to be made.
So also funding agency incentives, you need to do that.
But Peter, could I ask a question? Because you say it should be a community effort. So my question would be, which community? No, that's important, because I believe it will be in disciplinary communities. So like in the virtual physiological human, we are moving into a field where we have ontologies that can really classify and fully describe our models in terms of an XML. But we understand that within our community. I know that in other communities this is also happening. I think in Fusion you're also getting there big time. And that's helpful. Then underneath that there could be generic tools. That's interesting to explore. But I think, if we say the community, again, let's be specific. That is really helpful.
So to attempt to answer that question, there's only one thing that is not allowed to go in the Turing way, and that is a workflow that is domain specific. So the idea is that these should be interoperable processes that people can...
Why?
Because fair. Because,
That's not very fair to many communities.
Why not? Because if it's about not duplicating wasted effort.
So sometimes you can't be within the domain. So perhaps sometimes you have to do one, sometimes the other, I don't know. But I know a case where you can't be in one domain, and that's in the case of humanitarian assistance. So I've been to a few meetings with humanitarian organizations, and these people want to use modeling to help their activities. And whether it's aid deployment or trying to expect how many migrants arrive, or perhaps how they can better configure a refugee camp, for instance, they're going to rely on models. They're going to establish practices and standards. And you could say, oh, well, yeah, this is the humanitarian community. Yeah, but if you look at the simulation approaches and the academic disciplines that tie into that community, you end up with a very wide assortment of disciplines. So sometimes you have to go between the disciplines. And in fact, the humanitarian community, ironically, outside of academia, is now starting to assemble a process to actually vet these models for quality and to start to have a validation framework. And that's outside of the academic and outside of the commercial context. So yeah, sometimes you do have to step outside of that at least.
Any further thoughts on that?
Yeah, I think what we want to do is we want to take this level of like abstraction above, and we want to teach people like a generic project kind of setup. Like, it doesn't matter if your project's in biomedical or humanitarian. Like, there's basic questions that we ask ourselves every time we're setting up a project. Like, what is the research question? Why am I asking it? What do I hope to find out? Whatever. And we just want to create processes and checklists that help everyone. And that's why I say there's one thing that's not allowed in the Turing way, and it's domain specificity. Is because we want everybody to be able to use this resource and apply it to their own. Much like what it sounds like the humanitarian community are doing is that they're trying to like abstract this out outside of academia and outside of commercial settings in order to be able to validate their models. And yeah, that sounds pretty Turing way to me. I think that was your point.
So I'm keen that we get people to speak, and there's Colin MacDonald over there who's come into the UK, told me 2 weeks ago he's on 6 months sabbatical, works with a colleague of mine called Timo Betke, who was one of the organisers, unable to come. You stepped in, and you're a numerical analyst. What have you gained from this meeting?
Oh my, I didn't know I was going to be put on the spot. I don't think I'm standing in for Timo in any way here, but
I didn't mean standing in, but it's good that he brought you along.
Well, I've been interested in these ideas for a long time, mainly coming out of Randy Levesque's work, which was a name I haven't heard mentioned today, but that was a big sort of prime mover in reproducible research in my field. So I guess it's interesting to me to see how many other fields are now interested in this, and I think that's a really good thing. The other, I come from a free and open source software background outside of mathematics, so it's interesting to see how that has become so mainstream that we sort of take it for granted that the software will just be available. I think that's a major win. That certainly when I was a student was not the case. Most people's code was not available, and so in my opinion, there have been major victories, and clearly so much further to go.
All right, thanks, Colin. Any other thoughts? Because we're going to need to just go to the closing comments in a moment. I don't see anyone clamoring to say anything. Yes, Peter, go and say something.
Can I make one comment? Because I was thinking about why people don't do it. And of course, it's not free. It costs. Doing uncertainty quantification, putting error bounds on your outside, is going to cost you a lot of model runs. Your computer budget is going to be significantly smaller because you do this. And we have to factor that in to when we get the money. And we have to factor that into our ambition for what we're going to do. And we may have to lose resolution to do the ensemble to give you the uncertainty quantification. Clearly, if you're starting a model from scratch, you should build it in from the beginning. But we don't start models from scratch. Bits of models hang on for 50 years, and that's the way they are. And it's not free, and we have to accept it's not free. And some people will make the rational decision of not to spend the money to do it, and we have to encourage them that that's not the right thing to do. But it is something that does cost.
Very true. With that, then, let me ask you to join me in thanking the panel, but also yourselves for an active contribution to this discussion. Thank you very much indeed. It remains just to make a few closing remarks now, so the panelists can just return to their seats for a moment. Apostolos, I rely on you to set up my little set of slides there, and then we can be on our way. Remember, you'll be trapped in here over the weekend if you don't leave by 5:30. So we really were told to end at 5. Enough to read. Yeah, lots to read. We okay? Yeah. Brilliant. Fantastic. That looks good. Okay. So this is just to wrap up the session. Is it changing color? I think there's just a few comments to make here. At the beginning of the day, we said what we would be talking about. I liked the aspect of the Turing Institute in insisting that we ran the meeting in a particular fashion, so we had a lot of diverse types of discussions, not just people giving presentations, breakouts and chats over coffee and so on. I hope it's true that the event has been interesting for everybody. What we're talking about here is where things may go from here. And I just wanted to mention 2 or 3 things that are definitely happening which may be of interest to those who attended this meeting or are interested in follow-ups. One is that actually it was only yesterday that I got confirmation from the Royal Society Philosophical Transactions, which is mathematical, physical and computational Series A, that we have a theme issue confirmed on the topic of this conference, actually, reliability and reproducibility in computational science. And I've been talking to quite a few people for the last few months about whether they were willing to contribute to this thing, and many have said yes, and it's a mixed bag because you need to know that in order to make the proposal to the journal. And then some of the reviewers say, but you haven't given us all the details. But I'm not asking people to commit to write an article until we know we've been given the issue. Whatever, it's been offered to us now, so I'm going to come back to people. There are quite a few in this room who are already involved in that. The plan is for that publication to appear by the end of this year. So I'm still going to be hunting for a few contributions to that. It's a themed issue. A theme issue means a nice thing, which is a bit of a rarity in modern scientific publication, that the editors have total control, more or less, over what goes in. So it's not just research articles, it could be reviews, opinion pieces, and various things like that. So we would really like to make that an interesting publication. Other events that are relevant to us that I know of include a SIAM conference. It's actually going to take place in Garching, the same place where Onnie Luk comes from. And I think VECMA has a session on its own there, but there are plenty of other talks around uncertainty quantification there. Please look out for that. And one of the other conferences which connects us, we keep talking about the Dutch and Amsterdam, there's a connection there, but the International Conference on Computational Science is an annual sort of conference which has been running for 20 years. The 20th anniversary, as it were, meeting is this June in Amsterdam. And there are all kinds of tracks there, including multiscale modeling and uncertainty quantification. The deadline for submissions is the 6th of February, so if you're interested in contributing there, you've still got time to do it. And we, from the VECMA perspective, are very keen on continuing to work with those who have been supporting this meeting at the Turing Institute and others. So I'm hoping we will see plenty of things to come from combining our efforts in the future. Let me just thank a few people here. The organizing committee that helped to bring this event off, the names are there. You know most of them, if you didn't before, by dint of being in the meeting today. And I do want to make special thanks to those people who had to organize in great detail. And one of them is Jessie Wand, who's from the Alan Turing Institute, and they did a great job to promote the meeting. But also Apostolos Evangelopoulos, who's over there in the corner, who was working with me and did an awful lot to get this thing together. So can I ask you all to put your hands together and thank these guys? And I think, Apostolos, that's the last slide. So unless anyone's got something they want to say about where we're going, I want to be sure we do keep our interactions going. That's the message I'm giving. Anyone want to say something? If not, it remains for me to thank you all for coming and making this a great event. Have a good evening and safe travels back where you come from. Thank you. Bye-bye.